Look up at the night sky, at that breathtaking tapestry of stars and swirling galaxies, and you're seeing only the tiniest fraction of what's actually there. For every brilliant point of light, for every cosmic structure we can observe, there lies an infinitely deeper reality governed by powers we cannot see. This is the universe's greatest secret, a hidden architecture built by forces that work in the shadows, sculpting everything from the spin of an electron to the fate of a galaxy cluster. We are about to begin a journey to uncover these 30 unseen forces, the true architects of our cosmos. Think of the universe not as a collection of visible objects, but as a grand stage where the most crucial actors remain permanently in the wings. These are not merely ideas from the fringes of science, they are the fundamental principles that dictate the behavior of all reality. We feel their effects every single day, from the gravity that pins your feet to the ground to the light that warms your skin. Yet their origins and true natures are some of the most profound puzzles in all of human knowledge. This exploration will take us to the very edge of understanding, where the familiar laws of physics begin to warp and bend, revealing a cosmos far stranger and more magnificent than we ever conceived. We are going to move beyond the simple narratives of dark matter and dark energy, diving into the quantum foam where particles blink in and out of existence, traversing hypothetical higher dimensions curled up smaller than an atom, and witnessing the echo of the Big Bang itself in the faint afterglow of cosmic inflation. These forces are the invisible hands that wrote the rules of the game, the silent composers of the cosmic symphony. They are the reason our universe has structure, that life can arise, and that the vacuum of empty space teems with unimaginable energy. To understand them is to pull back the curtain on existence itself, to see the blueprints of reality. This is not just a tour of abstract concepts. It is a voyage to the heart of what it means to be part of this universe, to be a conscious piece of a cosmos that is actively being shaped by powers beyond our ordinary perception. So let's begin this journey together to meet the 30 unseen forces that are, right now, holding your world together and guiding the destiny of everything. Our journey into the unseen begins with the most famous invisible substance in the cosmos, dark matter. Picture a giant, spinning spiral galaxy like our own Milky Way. According to the laws of gravity as we understand them, stars on the outer edges of that galaxy, far from the central bulge of mass, should be moving much more slowly than those near the center. Think of our solar system. Pluto, way out on the fringe, orbits the Sun at a snail's pace compared to Mercury, which whips around at a blistering speed. Now apply that logic to a galaxy. But when astronomer Vera Rubin meticulously measured the velocities of stars in the Andromeda Galaxy in the 1970s, she found something that defied this expectation. The stars at the outer edges were moving just as fast as those near the center. It was as if the entire galaxy was spinning as a single, solid plate. The only plausible explanation was that the galaxy was embedded within an enormous, massive sphere of something invisible, a halo of matter whose gravity was pulling on those outer stars, speeding them up. This something neither emitted nor absorbed light. It interacted with the visible universe solely through the force of gravity. The evidence for this phantom substance had actually been glimpsed decades earlier by a brilliant and often contentious scientist named Fritz Zwicky. Back in the 1930s, Zwicky was studying the Coma Cluster, a vast collection of galaxies. He measured how fast these galaxies were moving around within the cluster and found their velocities were astonishingly high. So high, in fact, that the collective gravity from all the visible stars and gas in the cluster should have been completely insufficient to hold the cluster together. The entire system should have flown apart long ago. Zwicky concluded there must be a huge amount of unseen matter, which he called Dunkel Materie, or dark matter, providing the extra gravitational glue to keep the cluster intact. So what could this mysterious stuff be? It's not made of the atoms we know, protons, neutrons, and electrons that constitute everything you see around you. That familiar baryonic matter is just a small fraction of the cosmic budget. Dark matter is something else entirely, a new kind of particle that barely interacts with normal matter. Leading candidates include hypothetical particles with names straight out of a physics fantasy novel. One major group are WIMP, or weakly interacting massive particles. These are heavy particles that, as their name suggests, interact only via the weak nuclear force and gravity passing through our planet, and through you as if it weren't even there. Another compelling candidate is the Action, an incredibly light particle that was originally postulated to solve a different puzzle in particle physics. The hunt for these ghostly particles is one of the most dramatic efforts in modern science. It involves colossal machines like the Large Hadron Collider, smashing protons together at nearly the speed of light in the hope of actually creating a dark matter particle. Meanwhile, in ultra-quiet laboratories buried deep underground to shield them from cosmic rays, scientists wait patiently for the once-in-a-lifetime event, the infinitesimal recoil of a single atomic nucleus caused by a dark matter particle passing through and, against all odds, actually bumping into it. To truly grasp its importance, consider a computer simulation of the universe's evolution. If you run that simulation with only the gravity from the normal, visible matter we see in telescopes, you get a sparse, uninteresting cosmos. Galaxies never properly form, but when you add in the gravitational scaffolding of dark matter, something magical happens. A vast cosmic web emerges with filaments of dark matter stretching across billions of light years. Galaxies form at the dense intersections of this web, and their rotation curves match what Vera Rubin observed perfectly. Dark matter is not just a small component, it is the fundamental architecture upon which the entire visible universe is built, the hidden framework that allowed for our very existence. If dark matter is the cosmic glue holding galaxies together, then its counterpart, dark energy, is the enigmatic force determined to tear the entire cosmos apart. This discovery emerged not from a single brilliant insight, but from a patient, decades-long effort to measure the scale of the universe. For much of the 20th century, astronomers believed the expansion following the Big Bang must be slowing down. The collective gravitational pull of all the matter in the cosmos, they reasoned, would act as a brake, gradually decelerating the outward rush of galaxies. The big question was whether that deceleration would be enough to one day reverse the expansion in a big crunch, or if the universe would simply coast forever towards a cold, dark stillness. To find out, two independent teams set out in the 1990s to measure the expansion rate over cosmic time by observing a specific kind of stellar explosion. They used Type Ia supernova, which are the thermonuclear detonations of white dwarf stars. These events are crucial because they are standard candles. Each one reaches nearly the same peak brightness. By measuring how bright such a supernova appears from Earth and comparing that to its known intrinsic brightness, astronomers can calculate its distance with remarkable precision. Simultaneously, by analyzing the redshift of the supernova's light, how much its light waves have been stretched as the universe expands, they can determine how fast the galaxy hosting it was receding from us at the time of the explosion. By looking at supernova billions of light years away, these teams were effectively looking billions of years into the past, allowing them to chart how the expansion rate has changed over the lifetime of the cosmos. The results, announced in 1998, were staggering. The distant, ancient supernova were fainter than expected, meaning they were farther away than the prevailing model of a slowing expansion predicted. The only possible explanation was that the expansion of the universe was not slowing down at all, but accelerating. It was as if you threw a ball into the air, and instead of it falling back down, it shot away from you faster and faster, defying gravity itself. Something was overpowering the collective gravitational attraction of all matter, a mysterious repulsive force woven into the very fabric of space. This discovery immediately brought to mind an old idea from Albert Einstein. When he was formulating his theory of general relativity, his equations insisted that the universe should be either expanding or contracting. But the scientific consensus at the time, including Einstein's own belief, was of a static, unchanging cosmos. To force his equations to describe a static universe, he introduced a fudge factor, a repulsive term he called the cosmological constant, represented by the Greek letter lambda. Years later, after Edwin Hubble's observations confirmed the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder, and it was discarded for decades. Now it was back with a vengeance. The simplest explanation for dark energy is that it is the cosmological constant, a property of empty space itself. In this view, the vacuum is not truly empty. It seethes with a constant low-level energy density. As the universe expands and more space comes into existence, this vacuum energy increases, driving the expansion ever faster. The cosmological constant provides an elegant mathematical fit, but it leads to a profound and unsettling puzzle. When physicists try to calculate the expected energy of the vacuum based on quantum mechanics, the number they get is astronomically, impossibly large, about 120 orders of magnitude stronger than what we observe. This is arguably the worst prediction in the entire history of physics, suggesting our understanding of the quantum vacuum and gravity on cosmological scales is fundamentally incomplete. The implications of dark energy shape the ultimate destiny of everything. If the acceleration continues unabated, we are headed for a big freeze or heat death. In this scenario, the expansion becomes so rapid that the light from distant galaxies will one day be unable to reach us, leaving every galaxy isolated in an ever-darkening void. Star formation will cease as raw materials are spread too thin, and eventually all stars will burn out, leaving a cold, dark, and empty cosmos. This is not a fate reserved for some unimaginably distant future. The acceleration is already dictating the cosmic landscape. To unravel this mystery, new missions are dedicated to mapping the influence of dark energy with unprecedented precision. The European Space Agency's Euclid Space Telescope, for instance, is designed to create the most extensive and accurate 3D map of the universe ever made. It will observe billions of galaxies to trace how the cosmic web has evolved over time, measuring the subtle ways dark energy has fought against gravity to shape the large-scale structure of everything we see. So we have dark matter sculpting the cosmic architecture and dark energy controlling its ultimate expansion. But to truly grasp the forces at play in the universe, we have to zoom in to the very fabric of reality itself. This brings us to our third unseen force, a concept that completely redefines the meaning of nothing, the quantum field. Forget the idea of empty space as a passive, void stage where particles perform. Instead, picture a vast, invisible ocean. On a calm day, the ocean's surface appears flat and serene, but beneath that placid facade lies a realm of immense, chaotic energy, with currents and pressures constantly shifting and swirling. What we perceive as the vacuum of space is exactly like that. It is not truly empty. It is a seething, vibrant medium, a cosmic soup of fundamental entities known as quantum fields. These fields are the most fundamental reality, existing everywhere and for all time. What we call a particle, an electron, a quark, even the Higgs boson, is not a tiny, hard ball. It is merely a localized excitation, a tiny ripple or vibration in its respective underlying field. Think of it like a wave on our ocean. The wave is not a separate thing from the water. It is a manifestation of the water itself, a temporary disturbance moving through the medium. In exactly the same way, an electron is just a manifestation of the electron field. The field is the fundamental substance, and the particle is its fleeting signature. This isn't just a philosophical point. It's the bedrock of our most successful scientific theory ever, quantum field theory. This framework tells us that for every type of fundamental particle in the universe, there is a corresponding field that fills all of spacetime. There is an electron field, a quark field, a neutrino field, and so on. When a field is in its calmest, lowest energy state, we perceive that as empty space. But when energy is added to a specific point in that field, it excites it, and that excitation is what we detect and label as a particle. This explains something truly bizarre in the quantum world, the creation and destruction of particles. In particle accelerators, we don't smash bits of matter together. We add immense energy to these fields, causing them to produce new ripples, entirely new particles that weren't there before. The interactions between these particles, the forces that govern them, are also mediated by fields. The electromagnetic force, for instance, is carried by excitations in the electromagnetic field, which we call photons. When two electrons repel each other, they aren't magically pushing one another. Instead, one electron, a ripple in the electron field, interacts with the electromagnetic field, sending a ripple, a photon across to the other electron, which then responds. This constant, silent dance of fields and their excitations is what constructs our entire physical reality. The profound implication is that the vacuum of space, which seems like nothing, is in fact a tumultuous sea of potential. Due to the Heisenberg uncertainty principle, these fields can never be perfectly still. They are constantly experiencing fleeting fluctuations, with virtual particle-antiparticle pairs popping into existence and almost instantly annihilating each other. This quantum foam gives the vacuum a fundamental energy, a restless activity that is happening everywhere all the time, even in the deepest, darkest, most empty reaches of space between galaxies. So the very emptiness that dark energy seems to be harnessing is not empty at all. It is the most richly structured and active thing imaginable, the fundamental canvas upon which every single thing in the universe is painted. Now, if quantum fields provide the stage and the actors, our next unseen force provides a crucial piece of the plot. It gives many of those actors their substance. This is the Higgs field, and its discovery was one of the greatest scientific triumphs of the 21st century. For decades, the Higgs was the missing piece in the standard model of particle physics, the theoretical framework that describes all known fundamental particles and forces. The theory predicted that space is filled with an invisible field, now called the Higgs field, and that interactions with this field are what give particles their mass. But a prediction is one thing. Proving its existence was a monumental challenge that required building the largest, most complex machine humanity has ever constructed. That machine is the Large Hadron Collider at CERN, a 27-kilometer ring buried deep underground near Geneva, Switzerland. Inside this circular tunnel, protons are accelerated to within a whisper of the speed of light and then smashed together head-on. These collisions recreate, for a fleeting fraction of a second, the conditions that existed just after the Big Bang, unleashing immense energies that can cause the underlying quantum fields to ripple in very specific ways. The goal was to create a telltale ripple in the Higgs field itself, a particle known as the Higgs boson. Think of the field as an ocean, and the boson is a distinctive splash that proves the ocean is really there. For years, thousands of scientists analyzed the debris from countless trillions of these collisions, searching for a specific, rare signature among the subatomic shrapnel. Then on July 4, 2012, the announcement came. A new particle had been discovered, and its properties were consistent with the long-sought Higgs boson. It was a moment of profound validation, confirming a mechanism that shapes our very reality. So how does this field actually give particles their mass? A useful, though imperfect, analogy is to think of a famous celebrity trying to move through a crowded, excited party. As the celebrity moves across the room, they are constantly swarmed by admirers shaking hands, asking for autographs, and trying to take selfies. This interaction with the crowd slows them down significantly, making it difficult for them to accelerate and change direction. In this analogy, the partygoers represent the Higgs field. A fundamental particle moving through the universe is like a person moving through this room. Some particles, like photons, which are the particles of light, are like anonymous partygoers who no one notices. They slip through the crowd without interacting at all, and thus have no mass and travel at the speed of light. Other particles interact with the Higgs field intensely. The more a particle interacts with this field, the more it is slowed down, and this resistance to acceleration is what we experience and measure as mass. An electron has a small amount of mass, meaning it interacts with the Higgs field a little. The top quark, the heaviest known fundamental particle, interacts with the field so strongly it's as if the celebrity is the most famous person on the planet, barely able to move at all. This mechanism is not just a minor detail, it is absolutely fundamental for the existence of the universe as we know it. Without mass, the electron would not be able to be captured by a proton to form an atom. It would simply zip away at the speed of light. Without atoms, there would be no molecules, no stars, no planets, and certainly no us. The Higgs field is the cosmic molasses that allows matter to clump together, to form structures, and ultimately, to create a stable universe capable of harboring complexity and life. It is the unseen environment that gives substance to the visible world, turning ethereal quantum ripples into the tangible stuff of everything you have ever touched. But if the Higgs field gives particles their mass, what set the entire cosmic story in motion in the first place? To answer that, we must venture back to the very beginning, to the first fleeting fraction of a second after the Big Bang, where we encounter our fifth unseen force, cosmic inflation. The classic Big Bang theory is a story of a hot, dense, expanding universe, but it leaves some profound and puzzling questions unanswered. The first is known as the horizon problem. Look at the cosmic microwave background, the ancient afterglow of the Big Bang. No matter which direction you point your telescope, this relic radiation has almost exactly the same temperature, down to tiny variations of 1 part in 100,000. This is deeply strange. For two opposite sides of the observable universe to have reached this thermal equilibrium, heat would have had to travel between them, smoothing out the temperatures. But in the standard Big Bang model, there hasn't been enough time since the beginning of the universe for light or heat to have made that journey. It's as if you walked into a vast room where every single person, even those standing miles apart with no way to communicate, were all wearing the exact same outfit. The standard explanation simply doesn't allow for this uniformity to be established. The second major puzzle is the flatness problem. The geometry of our universe appears to be incredibly precisely flat. Not flat like a sheet of paper, but flat in the spatial sense, meaning the rules of Euclidean geometry we learned in school work perfectly over cosmic distances. The density of matter and energy in the universe seems to be perfectly balanced at a critical value, poised between a universe that would eventually collapse in on itself and one that would expand so rapidly it would tear itself apart. For the universe to be this flat 14 billion years later, its initial conditions at the Big Bang would have had to be fine-tuned to an astonishing degree of accuracy, like balancing a pencil on its tip for all eternity. The theory of cosmic inflation solves both of these problems in one grand, elegant sweep. It proposes that a split second after the universe began, a mysterious form of energy caused space itself to expand at an exponential, staggering rate. We're not talking about a fast expansion, we're talking about a growth so rapid it defies all intuition. In less than a trillionth of a trillionth of a trillionth of a second, a subatomic speck of the primordial universe was stretched to a size larger than our entire observable cosmos today. This hyper-expansion is the key. It tells us that the entire universe we can see today, from one horizon to the other, originally came from a tiny, microscopic patch that was in thermal contact before inflation blew it up. That's why the temperature is the same everywhere. It's because it was all once cozy and connected. the flatness problem is solved because inflation acts like someone taking a tiny, wrinkled piece of paper and stretching it to the size of a continent. No matter how crumpled or curved that original paper was, after such an immense stretching, any small section of it would appear perfectly flat to us. Our entire observable universe is just one such tiny, flat patch on a far grander cosmic fabric. So what was the engine behind this phenomenal growth? Physicists propose the existence of an inflaton field, a cousin to the Higgs field that permeated the early universe. For a brief moment, this field was trapped in a high-energy state, and its energy caused the fabric of space to repel itself, leading to the runaway expansion. As this field decayed and relaxed to its lower energy state, it dumped its immense energy into the universe, reheating it and filling it with the hot plasma of particles that would eventually form atoms, stars, and galaxies. But inflation did something even more remarkable. It didn't just create a smooth, flat universe, it also planted the seeds for all the structure we see today. Due to the quantum fluctuations inherent in any field, the inflaton field had tiny, random variations in energy across different points in space. Inflation then stretched these microscopic quantum wrinkles to astronomical sizes. Slightly denser regions where the inflaton field had a bit more energy became the gravitational seeds around which matter would later coalesce. These primordial imperfections, imprinted on the cosmos during its first moment, are the blueprints for everything, for galaxy clusters, for individual galaxies, for stars, and for planets. The best evidence for this incredible theory comes from the cosmic microwave background. While the temperature is incredibly uniform, sensitive telescopes like the Planck satellite have mapped the minuscule variations, the hot and cold spots, that correspond to those initial density fluctuations. Even more compelling is the search for a specific pattern in the polarization of this ancient light, a faint swirling signature known as B-mode polarization, which would be a direct imprint of the gravitational waves generated by the violent expansion of inflation itself. While definitive detection of this signal remains elusive, its pursuit is one of the most active frontiers in cosmology. Cosmic inflation is more than just a theory. It is a profound new vision of Genesis, where the largest structures in the cosmos were born from the tiniest quantum vibrations, all set into motion by an invisible force of unimaginable power that shaped the entire destiny of reality in the blink of an eye. From the grand sweep of cosmic inflation, we now dive into the quantum realm, to the very texture of spacetime, where the principle of ultimate uncertainty gives rise to one of the most bizarre and active forces shaping reality. This is the domain of quantum fluctuations. The Heisenberg uncertainty principle tells us there is a fundamental limit to what we can know about a particle's properties. You might have heard that you cannot know both its exact position and its exact momentum at the same time, but a more profound consequence deals with energy and time. It states that for an extremely brief interval, the energy within a region of space cannot be precisely defined. There is a built-in tolerance for error in the universe's ledger, and this allows for a spectacular loophole in the law of energy conservation. For fleeting moments, particles can spontaneously emerge from nothing, borrowing energy from the vacuum before annihilating each other and paying the energy back. This isn't a theoretical fantasy. It's a continuous, frantic activity happening in what you and I would call empty space. Every single cubic centimeter of the vacuum around you is a turbulent sea of these virtual particle-antiparticle pairs, electrons and positrons, quarks and antiquarks, constantly flickering in and out of existence. They are called virtual because they exist only for a time permitted by the uncertainty principle, far too short to be directly observed with our current technology. Yet, their ghostly presence has real, tangible, and measurable consequences that we can actually see in a laboratory. One of the most elegant demonstrations of this is the Casimir effect, named after the Dutch physicist Hendrik Casimir, who predicted it in the 1940s. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a perfect vacuum, parallel to each other. In the empty space outside the plates, any wavelength of virtual particles can pop into existence. But in the narrow gap between the plates, only certain wavelengths of virtual photons, the particles of the electromagnetic field, can fit, much like how only certain musical notes can resonate in a guitar string of a fixed length. This restriction means there are fewer possible virtual particle fluctuations happening in the gap between the plates than there are in the open space outside them. With more activity pushing on the outside surfaces of the plates than on the inside, the net result is an invisible, relentless pressure that forces the plates together. This is not some subtle theoretical prediction. It has been measured repeatedly with exquisite precision. It is the weight of the unseen, the literal force of nothingness pushing objects together. But the most profound role of these quantum jitters is written across the entire cosmos. Recall how the inflatoned field driving cosmic inflation was subject to its own inherent quantum fluctuations. At every single point in that primordial, rapidly expanding space, the energy density of the inflatoned field was jittering up and down thanks to these uncertainty-driven fluctuations. In regions where a random fluctuation caused a tiny bit more energy, the inflation would end a fraction of a moment later, leading to a slightly denser patch of universe. In regions with a bit less energy, inflation would end slightly earlier, creating a slightly less dense patch. Then, inflation performed its magic. It stretched these infinitesimal, quantum mechanical wrinkles in the field to sizes beyond our own galaxy. The microscopic became astronomical. These stretched fluctuations became slight variations in the density of matter and energy across the young cosmos. They were the primordial seeds of all structure. Over billions of years, gravity acted like a magnifying glass on these seeds. The slightly denser regions had slightly stronger gravity, pulling in more and more matter from their surroundings. The less dense regions were gradually emptied out. From this cosmic magnification process, the vast cosmic web emerged. The great walls of galaxies, the immense clusters, the swirling spirals, and the haunting voids. Every galaxy, every star, every planet, and by extension, every one of us, exists because of an unpredictable quantum tremor that occurred in the first fleeting moment of time, a tremor that was then frozen into the fabric of the universe by the phenomenal power of inflation. The grandest structures we can observe are therefore direct descendants of the smallest, most uncertain events permitted by the laws of physics. Yet, for all its transformative power, the quantum realm is not the only place where unseen forces rewrite the rules of reality. Let's turn now to a force so familiar we feel it every day, yet so profound its true nature remains one of the greatest insights in all of science: gravity. But we are not talking about the simple pulling force described by Isaac Newton. We are talking about Einstein's radical reimagining gravity, not as a force at all, but as the geometry of the universe itself, orchestrated by the gravitational field. The most famous way to picture this is the classic rubber sheet analogy. Imagine a vast, taut, flexible sheet of rubber representing the fabric of spacetime, a single entity combining the three dimensions of space with the one dimension of time. Now place a heavy bowling ball in the center of this sheet. The ball creates a deep, smooth depression in the rubber. This is mass warping spacetime. The bowling ball represents a massive object like our sun. If you then take a much smaller, lighter object like a marble and set it rolling near the bowling ball, it won't travel in a straight line. Instead, it will spiral inward, tracing a curved path around the heavy object, eventually falling into the depression. From a bird's eye view, it looks as if the bowling ball is pulling the marble toward it. But there is no pull. The marble is simply following the simplest path through the curved landscape created by the heavy mass. This is the essence of general relativity. Mass and energy tell spacetime how to curve, and the curvature of spacetime, in turn, tells mass and energy how to move. What we feel as the force of gravity is just our experience of moving through this warped geometry. Think about driving a car on a perfectly straight, flat highway. Your steering wheel stays centered. Now, imagine that highway is built on the side of a large, gentle hill. To stay on the road, you have to constantly turn the wheel, feeling a pull toward the side. The car isn't being actively pulled by an invisible force. It is simply following the curved path of the road. In the same way, Earth orbits the Sun not because the Sun is magically tugging on it across empty space, but because our planet is following a geodesic, the straightest possible path through the curved spacetime surrounding the Sun. This geometric picture of gravity makes predictions that sound like science fiction, but have been confirmed again and again. The most dramatic manifestation is the black hole, a region of spacetime where the curvature becomes so extreme that nothing, not even light, can escape. In our rubber sheet analogy, this would be like the bowling ball becoming so impossibly heavy that it tears through the sheet, creating an infinitely deep pit with steep sides. The point of no return is the event horizon, the boundary beyond which all paths lead inward. Another stunning effect is gravitational lensing. Just as a curved piece of glass can bend light to magnify or distort an image, a massive object like a galaxy cluster curves the spacetime around it so profoundly that it acts as a cosmic lens. Light from a distant galaxy traveling toward us on a straight path through this warped space is bent from its original trajectory. From our viewpoint, this can create multiple images of the same galaxy, or stretch it into bright, sweeping arcs of light called Einstein rings. Astronomers now routinely use this effect to study objects that are otherwise too far away or too faint to see, letting the gravity of foreground galaxy clusters do the work of a natural telescope. This unseen gravitational field, this curvature of reality itself, is not a static stage. Ripples in this field can travel across the universe. When two massive objects like black holes or neutron stars spiral into each other, they create violent oscillations in the fabric of spacetime, sending out waves of curvature that propagate at the speed of light. The detection of these gravitational waves by the LIGO and Virgo observatories opened up an entirely new way of observing the cosmos, allowing us to hear the collisions of invisible giants. So the next time you drop your keys, remember that they are not being pulled down by a mysterious force. They are simply sliding effortlessly and inevitably along the invisible contours of a universe bent by the mass of the entire planet beneath your feet, following a path written into the very geometry of existence. While gravity sculpts the cosmos on the grandest scales and quantum forces choreograph the subatomic dance, there is another unseen power that is arguably the artist of our daily reality, painting the world with color, binding matter together, and making life itself possible. This is the electromagnetic force, and its influence is so pervasive that almost every experience you have, from the warmth of sunlight on your skin to the solidity of the floor beneath your feet, is a direct consequence of its silent, invisible work. To understand its scope, consider the simple act of seeing these words. Light, a visible manifestation of electromagnetism, travels from your screen, enters your eyes, and triggers electrical signals in your brain, allowing you to perceive the world. But light is just one tiny slice of a much broader spectrum, all born from the same fundamental field. At its heart, electromagnetism is the force that governs the behavior of electrically charged particles. Positive and negative charges attract one another, while like charges repel. This simple rule, acted out through an unseen field, is the engine of chemistry, the architect of materials, and the reason atoms can even exist. An atom is a miniature solar system with a positively charged nucleus at the center and negatively charged electrons whizzing around it. The electromagnetic attraction between the opposite charges of the nucleus and the electrons is what holds the entire structure together. Without it, the electrons would simply fly off into space, and matter as we know it would instantly disintegrate into a formless cloud of particles. This force is communicated through the electromagnetic field, and its messenger particle is the photon. When two electrons repel each other, for instance, they are not magically pushing one another across a distance. Instead, one electron, by virtue of its charge, disturbs the electromagnetic field, sending a ripple through it, a virtual photon, that travels to the other electron, instructing it to move away. This constant light-speed exchange of photons is the unseen dialogue that dictates the structure of every molecule and the properties of every material. The strength of this electromagnetic conversation is not arbitrary. It is precisely set by one of the most mysterious and important numbers in all of physics, the fine structure constant. This pure, dimensionless number, roughly equal to 1/137, defines the strength of the interaction between charged particles and light. It is a fundamental constant of nature, and its value is a profound enigma. Why is it this specific number and not something else? Physicists have calculated that if the fine structure constant were even slightly different, the universe would be unrecognizable. A few percent larger, an atomic nuclei would not be able to hold onto their electrons, preventing the formation of stars. A few percent smaller, and the complex nuclear reactions that power stars would fail. This number sits in a razor-sharp sweet spot that allows for the existence of carbon, oxygen, and the complex chemistry necessary for life. It is a universal setting, fine-tuned with breathtaking precision, governing the intensity of the electromagnetic force that shapes our reality. We can visualize the influence of this force through its field lines, an elegant conceptual tool developed by Michael Faraday in the 19th century. While these lines are not physically real, they provide a powerful map of the field's influence. Imagine sprinkling iron filings around a bar magnet. The filings naturally align themselves along the magnetic field lines, tracing out beautiful, curved arcs from the north to the south pole. These lines represent the direction and strength of the magnetic force. The closer the lines are together, the stronger the force. For an electric charge, the field lines radiate outward in all directions, like the spines of a sea urchin. These invisible architectures of force guide charged particles along specific paths, dictating the flow of electric current in a wire and holding our galaxies' spiral arms together through immense magnetic fields that weave between the stars. The most spectacular demonstration of the electromagnetic field's power is the vast spectrum of radiation it generates. Whenever a charged particle is accelerated, whether it's an electron jiggling in a hot object or one vibrating wildly in an atomic nucleus, it radiates energy in the form of electromagnetic waves. The only difference between the gentle radio waves that carry music to your car, the warming infrared light from a heater, the visible light that paints a rainbow, the penetrating X-rays that reveal our bones, and the deadly gamma rays from a cosmic explosion is the frequency of their oscillation. They are all the same fundamental phenomenon, ripples in the same electromagnetic field, distinguished only by the energy they carry. This cosmic symphony of radiation fills every cubic inch of the universe, a constant, unseen torrent of information and energy flowing through us, connecting us to the most violent and tranquil events across the cosmos, all orchestrated by the silent, pervasive hand of electromagnetism. But for all the power of electromagnetism to build atoms, there's a fundamental problem at the very heart of matter that threatens to tear it all apart. Inside every atomic nucleus, you have a crowd of positively charged protons, all crammed incredibly close together. According to the electromagnetic force we just discussed, these identical charges should violently repel each other, blasting the nucleus to pieces in an instant. And yet they don't. Your body, the ground you stand on, the very air you breathe, all of it is stable. Something far stronger than electromagnetism must be at work, gluing the nucleus together against its own internal rebellion. This is the domain of the strong nuclear force, the most powerful fundamental force in the universe, but one so short-ranged its influence barely extends beyond the width of a single atomic nucleus. Its story begins not with protons and neutrons, but with something even more fundamental. Protons and neutrons are not themselves elementary particles. They are each made up of triplets of smaller entities known as quarks. It is here, at this deepest level, that the strong force truly originates. The theory that describes it is called quantum chromodynamics, or QCD, a name that hints at its central mechanic, chromo meaning color. In QCD, quarks carry a type of charge whimsically called color charge. This has nothing to do with visual color. It's just a convenient way to describe a property that comes in three types, which physicists labeled red, green, and blue. Just as the electromagnetic force acts between electrically charged particles, the strong force acts between color-charged particles, but there's a profound difference. While you can have a positive or negative electric charge existing on its own, quarks can never be found in isolation. They are forever bound together in combinations that are colorless or white, much like how mixing red, green, and blue light together produces white light. This leads to one of the most bizarre phenomena in all of physics: confinement. Imagine quarks are connected by a rubber band of pure energy. If you try to pull two quarks apart, the energy in this rubber band increases. Pull them just a little and it stretches easily, but try to separate them further and the energy stored in the bond becomes so immense that it spontaneously creates a new quark-antiquark pair from the vacuum, leaving you with two new color-neutral particles instead of a single free quark. It's as if you are trying to pluck a single strand from a rope, but the rope simply grows a new end, forever frustrating your attempt at isolation. Because of confinement, we can never observe a lone quark. They are permanently imprisoned within composite particles like protons and neutrons. The particles that mediate this incredibly strong color force are called gluons. Think of them as the subatomic world's ultimate superglue. While the photon that carries the electromagnetic force is massless and chargeless, a gluon is also massless, but it crucially carries color charge itself. This is a game-changing distinction. A photon, being neutral, does not interact with other photons, but a gluon, since it carries color, can and does interact with other gluons. This self-interaction is what makes the force so powerful and leads to confinement. The gluons don't just ferry the force between quarks, they form dense, roping streams of energy between them, creating the unbreakable bonds that hold the quarks in place. This gluon-mediated force between individual quarks is the primary, fundamental strong force, but its influence doesn't stop there. A residual effect of this quark-binding force leaks out beyond the boundary of a proton or neutron, creating a secondary nuclear force. It is this residual strong force that acts as the nuclear glue, binding protons and neutrons together to form atomic nuclei. This force is what overcomes the fierce electromagnetic repulsion between protons, allowing for the existence of all the elements in the periodic table heavier than hydrogen. Without this unseen nuclear cement, our universe would be a boring sea of hydrogen single protons orbited by electrons, with no complexity, no chemistry, and no life. A stunning and counterintuitive feature of the strong force discovered in the 1970s is a property known as asymptotic freedom. It seems to defy all logic. As you bring two quarks extremely close together, as you might in a particle collider by smashing them with tremendous energy, the strength of the strong force between them actually weakens. At these tiny distances, the quarks and gluons behave almost as free, non-interacting particles. It's as if the superglue becomes as slippery as water when the quarks are pressed cheek to cheek. This is why we can study them at all in high-energy experiments, but as they begin to separate, the force quickly grows stronger, snapping them back into confinement. This dual nature, asymptotic freedom at short distances and confinement at large distances, is the unique signature of the strong force, and the reason it forges the unshakable foundations of the visible world. While the strong force builds the indestructible atomic nucleus, there is another, more subtle nuclear force at work, one that specializes in transformation and decay. This is the weak nuclear force, and despite its name, its influence is anything but feeble. It is the master of change, the force that allows one type of particle to morph into another, a process that is absolutely essential for the existence of nearly every element in the universe and the very energy that powers the stars. Its most familiar manifestation here on Earth is radioactive decay. Take a lone neutron, for instance. Left to its own devices outside an atomic nucleus, a neutron is not stable. In a matter of minutes, it will spontaneously transform. It turns into a proton, and in the process, it spits out an electron and an almost ghostly particle called an antineutrino. This process, known as beta decay, is orchestrated entirely by the weak force. It's what makes certain elements like uranium radioactive, as their large, unstable nuclei use this mechanism to slowly shift their balance of protons and neutrons, moving step by step toward stability. But the true cosmic power of the weak force is revealed not in decay, but in creation, deep within the heart of our Sun. The Sun's immense energy comes from nuclear fusion, the process of forcing atomic nuclei together. But there's a fundamental problem at the very first step. To begin the main fusion cycle, known as the proton-proton chain, two protons must overcome their powerful electromagnetic repulsion and get close enough for the strong force to bind them. However, if you just fuse two protons, you get a nucleus with two protons and nothing else, a helium-2 nucleus, which is violently unstable and immediately flies apart. For the Sun to shine, one of those protons has to fundamentally change its identity. This is where the weak force performs its magic. Very rarely, when two protons are squeezed incredibly close together in the Sun's core, the weak force intervenes. It allows one of the protons to turn into a neutron. This transformation is mediated by the exchange of a particle called a W boson. The proton, which is made of two up quarks and one down quark, emits a positively charged W boson. This changes one of its up quarks into a down quark, transforming the proton into a neutron. The emitted W boson then almost instantly decays into a positron, the antimatter counterpart of an electron and a neutrino. This newly formed neutron can now bind with the remaining proton to create a stable deuterium nucleus, the first crucial step in building helium and releasing the energy that has bathed our planet for billions of years. What makes this force so uniquely weak and short-ranged compared to the electromagnetic force? The answer lies in its messenger particles. While the electromagnetic force is carried by the massless photon, which can travel across the universe, the weak force is carried by three massive particles, the W positive, W negative, and Z0 bosons. These particles are extraordinarily heavy, each weighing almost as much as a whole atom of iron. According to quantum principles, a force carrier particle can only exist for a fleeting time, dictated by the Heisenberg uncertainty principle. The more massive the particle, the shorter its allowed lifetime and the shorter the distance it can travel. This is why the weak force's influence is confined to a range smaller than the diameter of a proton. Its massive messengers are simply too heavy to get very far, making it a profoundly intimate force, acting only on the tiniest of scales. This intimate connection to mass leads to a profound link with another unseen force we've discussed, the Higgs Field. It is the interaction of the W and Z bosons with the Higgs field that gives them their immense mass. Without the Higgs mechanism, these bosons would be massless like the photon, and the weak force would have a long range, utterly changing the rules of nuclear physics and likely making a stable universe like ours impossible. The weak force also holds a deeply strange and unique property that sets it apart from all other fundamental forces. It violates parity symmetry. For gravity, electromagnetism, and the strong force, the laws of physics are mirror symmetric. If you were to watch a recording of any interaction governed by these forces and then watch its mirror image, you would not be able to tell which was the original and which was the reflection. The weak force shatters this mirror. In the 1950s, physicist Qin Sheng Wu conducted a brilliant experiment using cobalt-60 atoms which decay via the weak force. She demonstrated that the electrons emitted in the decay were not flung out randomly. They had an overwhelming preference to fly out in a direction opposite to the spin of the nuclei. If you looked at this process in a mirror, the relationship would reverse and the experiment would look fundamentally different. The weak force, therefore, possesses a built-in handedness. It can distinguish between left and right. This profound asymmetry, written into the laws of the universe at the most fundamental level, may even hold the key to one of cosmology's great mysteries: why the universe we see is made almost entirely of matter with very little antimatter. The weak force's preference for one-handedness over the other may have subtly influenced the early cosmos, tipping the scales in favor of the matter that now forms every star, planet, and person. Now, as we explore this network of unseen forces, we come to one of the most mind-bending phenomena in all of physics, a concept that so troubled Albert Einstein he famously dismissed it as spooky action at a distance. This is the realm of quantum entanglement, where the very definitions of separation and individuality break down. To grasp its strangeness, imagine you have a pair of magical dice. You take one die with you on a journey to a distant galaxy, while your friend keeps the other here on Earth. The moment you roll your die and see it land on a 3, you know instantly, with absolute certainty, that your friend's die has also just shown a 3. This instantaneous connection, this mysterious coordination, is the essence of entanglement. In the quantum world, this isn't magic, it's a verified property of nature. Two or more particles can be created or interact in such a way that they become a single, unified quantum system. Describing one particle without the other is impossible. Their fates are intertwined. We say their quantum states are linked. This could be their spin, their polarization, or their momentum. The truly baffling part is what happens when you measure one of these entangled particles. The act of measurement forces the particle to choose a definite state from a cloud of probability, and at that exact moment, its entangled partner, no matter if it's in the next room or on the other side of the observable universe, immediately assumes the corresponding state. This influence appears to happen instantaneously, seemingly faster than the speed of light. This is what Einstein found so objectionable, as it seemed to violate the cosmic speed limit set by his own theory of relativity. He believed there must be some hidden variables, some deeper, unseen properties determined at the moment of entanglement that would explain the correlation without any spooky long-distance communication. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised an ingenious mathematical theorem that could, in principle, test whether local hidden variables could explain the phenomenon. Later experiments, most famously by Alain Aspect and his team in the 1980s, put Bell's idea to the test. They created pairs of entangled photons and measured their properties along different axes. The results were conclusive. The correlations between the particles were stronger than any local hidden variable theory could possibly allow. The universe had chosen spookiness. Since then, entanglement has been demonstrated over and over across distances of hundreds of kilometers, even between a particle on the ground and one in an orbiting satellite. The connection is real, and it forces us to radically reconsider the nature of reality itself. It suggests that at a fundamental level, the universe may not be composed of separate, independent objects, but is instead a deeply interconnected whole. The properties we measure aren't local and pre-existing. They are relational, emerging from a web of connections that transcend space. This profound interconnectedness isn't just a philosophical curiosity, it's the foundation for revolutionary new technologies. One of the most promising is quantum computing. Ordinary computers use bits which are either a 0 or a 1. Quantum computers use quantum bits or qubits which can be a 0, a 1, or both at the same time, a state known as superposition. When you entangle multiple qubits, their computational power grows exponentially. A calculation that would take a classical computer thousands of years could be solved by a sufficiently powerful quantum computer in a matter of hours, with potential breakthroughs in drug discovery, materials science, and artificial intelligence. The other major application is quantum cryptography, specifically a method called quantum key distribution. Because measuring an entangled particle disturbs its state, any attempt to eavesdrop on a quantum encrypted message immediately alerts the sender and receiver. This allows for the creation of theoretically unbreakable codes, securing our digital communications in a future where classical encryption may fail. What entanglement ultimately teaches us is that our classical intuition about the world, where objects have defined properties and influences travel smoothly through space and time, is only a surface-level approximation. Beneath that familiar reality lies a quantum substrate where separation is an illusion, and the entire cosmos might be woven together by invisible threads of instantaneous connection. But this simple and elegant idea that empty space has its own innate energy leads directly to one of the most embarrassing and profound puzzles in all of modern science, the cosmological constant problem. When physicists attempt to calculate how much energy this quantum vacuum should contain, the answer they get is not just a little bit off, it is catastrophically, unimaginably wrong. The calculation involves adding up all the fleeting energy from those quantum fluctuations, the virtual particles popping in and out of existence in every cubic centimeter of space. The result is a number so enormous it defies comprehension. The theoretical prediction exceeds the observed value of dark energy's density by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To put that number in perspective, it is greater than the number of atoms in the entire observable universe. This isn't just the worst prediction in the history of physics. It is a screaming anomaly that tells us, in no uncertain terms, that something is fundamentally missing from our understanding. Either our theory of the quantum vacuum is deeply flawed, our theory of gravity on cosmic scales is incomplete, or there is some incredible cancellation mechanism at work that we have not yet discovered. This cosmological constant problem is not a minor technicality. It is a gaping chasm at the intersection of our two most successful theories, quantum field theory and general relativity, and bridging that chasm is perhaps the single greatest challenge in fundamental physics today. The sheer magnitude of the error suggests that we are missing a monumental piece of the puzzle, a principle that somehow reconciles the frantic energy of the quantum world with the serene, large-scale behavior of the cosmos. Some physicists speculate that the answer may lie in the concept of the multiverse. In this provocative view, our universe is just one of a vast, perhaps infinite, ensemble of universes, each with different fundamental constants and laws of physics. In most of these universes, the cosmological constant is enormous, and those universes either fly apart too quickly for anything to form or collapse back on themselves instantly. We, of course, find ourselves in one of the rare, finely tuned universes where the cosmological constant is small enough to allow for the formation of galaxies, stars, planets, and life. While this anthropic explanation is philosophically unsettling for many, as it suggests the fundamental laws of our universe may be a random accident, it remains one of the few frameworks that can accommodate such an immense numerical discrepancy. Other theories seek a more deterministic solution, proposing new physical principles or undiscovered symmetries that would force the vacuum energy to be exactly zero or the very small value we observe. Supersymmetry, a popular theoretical extension of the Standard Model, predicted that every known particle has a superpartner. If this symmetry were unbroken, the contributions of these partner particles to the vacuum energy would perfectly cancel out the contributions of the ordinary particles, resulting in a net energy of zero. However, we have not found these superpartner particles at the energies we've probed, meaning supersymmetry, if it exists, is a broken symmetry, and the perfect cancellation is ruined, leaving us with a large, unexplained remainder. The mystery of the cosmological constant is a humbling reminder of how much we have yet to learn. It represents a fundamental disconnect between the world of the very small and the world of the very large. Dark energy, in the form of this tiny but persistent vacuum energy, is the dominant force shaping the ultimate fate of our cosmos, yet we cannot explain why it has the value it does. Its discovery forced the cosmological constant out of the dustbin of history and back into the spotlight, not as Einstein's blunder, but as arguably the most important unsolved problem in all of physics. Venturing now from the well-trodden paths of established physics, we arrive at a concept that pushes the very boundaries of our imagination: torsion fields. So far, we've explored how mass and energy curve spacetime, creating what we experience as gravity. But what if that fabric could do more than just bend? What if it could also twist? This is the core idea behind torsion, a theoretical extension of Einstein's general relativity that proposes spacetime itself can possess a kind of intrinsic twisting, a rotational stress in addition to its curvature. Think of it this way: if general relativity describes the landscape of the universe as a gently sloping rubber sheet, torsion suggests that this sheet can also be locally coiled, like a phone cord or a spiraling strand of DNA. This twisting isn't generated by mass alone, but by something even more fundamental to matter: the intrinsic spin of elementary particles. Every electron, every quark, every fundamental component of reality possesses this property of quantum mechanical spin. In the framework of torsion theories, it is this microscopic spinning that acts as the source for these hypothesized twists in the geometry of spacetime. While Einstein's gravity connects to the energy and momentum of matter, torsion connects directly to its spin-angular momentum, proposing a new and deeper link between the quantum world and the large-scale structure of the cosmos. Some of the most intriguing, though highly speculative, applications of this idea attempt to tackle the very mysteries we've already discussed. Could torsion hold the key to dark energy? One compelling line of thought suggests that on cosmological scales, the collective twisting of spacetime from all the spinning particles in the universe could produce a constant repulsive effect. This universal torsion would act as a kind of cosmic anti-twist, pushing galaxies apart and driving the accelerated expansion we observe, all without the need for a cosmological constant or vacuum energy. In this scenario, dark energy isn't a property of empty space, but a dynamic consequence of the spin-saturated fabric of the universe itself. Another fascinating and controversial application lies in the realm of propulsion. If we could somehow generate and control a powerful, localized torsion field, the theory suggests we might be able to manipulate the inertia of an object or even create a warp drive effect. The concept involves creating a twist in spacetime that would, in essence, allow a spacecraft to surf on a wave of distorted geometry, reducing or eliminating the need for conventional propellant. This is the kind of idea that fuels dreams of interstellar travel, but it's crucial to understand the current scientific standing. Torsion remains a fringe concept, largely explored in the domain of alternative theories, and not yet incorporated into the mainstream standard model or general relativity. No experiment has provided conclusive evidence for the existence of these fields in a form that would produce detectable forces or propulsion effects. The immense gravitational fields of neutron stars and black holes, where such effects should be most pronounced, have so far shown no unambiguous signs of torsion's influence. The mathematics involved is extraordinarily complex, and the predicted effects are often incredibly weak, making them exceptionally difficult to test with our current technology. This places torsion fields in a fascinating category, a theoretically possible, mathematically coherent extension of our understanding of gravity that currently lives on the frontier of physics. It represents the creative, boundary-pushing spirit of scientific inquiry, a bold what-if that challenges us to look at the universe in a completely new way. Whether it remains a mathematical curiosity or one day becomes a cornerstone of a new theory of everything, it reminds us that our map of reality is still being drawn, and the most profound discoveries may lie in the twists we have yet to uncover. This brings us to the very engine behind that phenomenal period of cosmic inflation, a hypothetical but profoundly influential entity known as the inflaton field. We introduced it as the driving force, but to truly appreciate its power, we need to understand its nature. Like the Higgs field, the inflaton is what physicists call a scalar field. This simply means that at any given point in space, this field has a magnitude, a strength, but no inherent direction. Think of it like the temperature in a room. At every location, you can assign a single number representing how hot or cold it is. The Higgs field is like that, giving particles their mass, and the inflaton field is believed to be another such field that permeated the entire infant cosmos. In the universe's first fleeting moment, this field was trapped in what's known as a false vacuum state, a high-energy condition that was temporarily stable, but not truly the lowest energy state it could achieve. Imagine a grand, cosmic landscape of hills and valleys representing different energy levels. The inflaton field started out perched high up on a very flat plateau on this landscape. This position, high above the ultimate valley floor, meant the field possessed an immense potential energy density. And according to Einstein's equations, any form of energy causes spacetime to repel itself. This is the critical trigger. While the inflaton field remained stuck on that high plateau, its enormous potential energy acted as a form of anti-gravity, causing the fabric of space itself to expand at an exponential, staggering rate. This wasn't a gentle pushing apart, it was a runaway repulsion, doubling the size of the universe again and again in intervals of time so short they are almost meaningless to the human mind. In less time than it takes for light to cross a single proton, a subatomic speck of reality was stretched to a size larger than our entire observable universe today. But this incredible state couldn't last forever. Just as a marble resting on a high, flat plateau will eventually find a slight slope and begin to roll, the inflaton field began a slow, quantum mechanical process known as rolling down its potential energy landscape. As it rolled, it gradually converted its stored potential energy into kinetic energy. This rolling phase is when the most rapid expansion occurred. Eventually, the field reached the steep part of the slope and accelerated, finally falling into the true vacuum valley at the bottom. This was the end of inflation, but the story doesn't end with the field settling down. The crucial final act was something called reheating. All that kinetic energy the inflaton field gathered on its way down the hill had to go somewhere. As the field oscillated around the bottom of the valley, like a ball bouncing back and forth after a fall, it decayed explosively. In a magnificent cascade of energy, the inflaton field dumped all of its remaining energy into the creation of particles. It essentially repopulated the entire universe, which had been left cold and empty by the incredible stretching of inflation, filling it with a hot, dense, and seething plasma of quarks, leptons, photons, and all the fundamental building blocks of matter. This reheating event was the true Big Bang in many ways, setting the initial conditions for the hot universe described by the Standard Model. The temperature and density of this newly created plasma were perfectly set to allow for the formation of atomic nuclei and eventually everything we see around us. So, while we have never directly detected the inflaton field, its proposed role is absolutely foundational. It took a singularity and transformed it into a vast, smooth, and flat cosmos, And then, in its dramatic decay, it provided all the raw material, every single particle that would go on to form every star, every planet, and every one of us. It is the ultimate unseen sculptor whose brief, powerful existence wrote the opening chapter to the entire history of our universe. From the twisting geometry of spacetime to the explosive birth of the cosmos, we have charted unseen forces that sculpt reality on the grandest scales. But to truly unite these cosmic phenomena with the frantic quantum world, we must venture into the realm of the purely hypothetical, to a particle that has never been detected but is fundamental to our dreams of a complete physical theory. This is the graviton, the proposed messenger particle of gravity. We have seen how general relativity masterfully describes gravity as the curvature of spacetime, a beautiful geometric picture. And we have explored the quantum field theory framework, where the other three fundamental forces, electromagnetism, the strong force, and the weak force, are all transmitted by the exchange of force-carrying particles, photons, gluons, and the W and Z bosons. This creates a profound schism in our understanding of the universe. We have two incredibly successful but seemingly incompatible theories. To bridge this gap and create a single, unified description of nature, physicists believe gravity must also be quantized. It must have its own quantum field and its own associated particle. That particle is the graviton. In this theoretical picture, just as two electrons repel each other by exchanging virtual photons, two masses attract each other by exchanging virtual gravitons. The gravitational field would not be a static geometric landscape, but a dynamic quantum field humming with these messenger particles. The proposed properties of the graviton are dictated by the nature of the force it carries. Because gravity is incredibly long-range and acts on everything that has energy, the graviton must be massless, just like the photon, allowing it to travel across the universe. It must also be chargeless, since gravity only attracts. There is no such thing as negative gravity that would cause repulsion in the same way negative electric charges do. The most telling property, however, is its spin. In the quantum world, particles have an intrinsic angular momentum known as spin, and the spin of a force-carrying particle determines the character of the force. The photon, carrier of electromagnetism, has a spin of 1. The graviton, by contrast, is predicted to have a spin of 2. This difference in spin is why gravity is always attractive and why it couples to energy itself, not just to a specific charge. It is this spin 2 property that allows the graviton, in the low energy limit, to reproduce the curved spacetime of general relativity. The mathematics suggests that the collective behavior of countless gravitons would weave the fabric of spacetime itself. So why, if this particle is so central to our theoretical understanding, have we never found one? The challenge is almost incomprehensibly immense and boils down to one simple fact: gravity is staggeringly weak. To appreciate this weakness, consider a small fridge magnet. The electromagnetic force from that tiny magnet is powerful enough to overcome the gravitational pull of the entire Earth, lifting a paperclip against the planet's immense weight. This incredible disparity in strength translates directly into the difficulty of detecting a single graviton. The probability of a graviton interacting with a particle of matter is so vanishingly small that it makes the already difficult hunt for dark matter particles look straightforward by comparison. Any experiment designed to detect a single graviton would need to be so massive and so sensitive that it borders on the impossible with current technology. The energy required to create and observe a single graviton in a particle collider is thought to be trillions of times greater than what the Large Hadron Collider can achieve, requiring an accelerator the size of a galaxy. This is why we primarily search for indirect evidence, such as the primordial gravitational waves from inflation, which are themselves a macroscopic manifestation of countless gravitons. The detection of a graviton would be one of the most monumental achievements in the history of science, a discovery that would undoubtedly warrant a Nobel Prize. It would provide the final, missing piece of the quantum puzzle, proving that all four fundamental forces operate under the same quantum rules. This would be the ultimate validation of a quantum theory of gravity, bringing us to the threshold of a theory of everything. Such a theory would seamlessly weave together the vast cosmic dance of general relativity with the intricate subatomic choreography of quantum mechanics, giving us a single, elegant equation or set of equations capable of describing every physical phenomenon in the universe, from the birth of a cosmos to the spin of an electron. The graviton is more than just a hypothetical particle. It is the holy grail of modern physics, the key that could unlock the deepest secrets of existence and reveal the final, unified symphony of reality. We have journeyed through the ghostly realms of dark matter and the transformative power of the weak force, but among the most compelling candidates for that invisible cosmic scaffolding is a particle born from an entirely different puzzle, one rooted in the strange symmetries of the strong nuclear force. This is the action, a hypothetical entity so light and elusive it makes other dark matter candidates seem almost bulky by comparison. Its story begins not with cosmology, but with a deep and subtle mystery in the laws of particle physics known as the strong CP problem. The C and P here stand for charge and parity, two fundamental symmetries. For a long time, physicists believed that the laws of nature were symmetric under the combined operation of swapping a particle with its antiparticle. That's charge conjugation, and viewing its reflection in a mirror, that's parity. We already saw how the weak force violates this CP symmetry, which is why we have a matter-dominated universe. But what about the strong force which holds atomic nuclei together? The mathematics of the strong force, quantum chromodynamics, naturally allows for a term that would violate CP symmetry. This term would have profound and bizarre consequences. It would cause the neutron, which is electrically neutral, to possess a tiny, separate electric dipole moment, a kind of internal positive-negative charge separation, like a microscopic bar magnet but for electricity instead of magnetism. This may sound minor, but its effects would be anything but. If this CP-violating term existed at the size the math allows, it would drastically alter the properties of neutrons and the nuclear reactions that forge the elements. The universe as we know it could not exist, yet when physicists measure the neutron's electric dipole moment with exquisitely sensitive experiments, they find it to be zero to an astonishing degree of precision. The question is, why? Why is this CP violation for the strong force so perfectly tuned to zero, cancelling out with such incredible precision? It appears as if nature has gone out of its way to hide this effect, and physicists Roberto Pexi and Helen Quinn proposed a beautifully elegant solution. They suggested that this troublesome CP violating term isn't actually a fixed constant, but can be dynamically cancelled out by a new field that pervades the universe. Shortly after, physicists Frank Wilczek and Steven Weinberg realized that this Pexi-Quinn mechanism would have a physical consequence, a new, very light particle. Wilczek named it the action after a brand of laundry detergent because it cleaned up the strong CP problem so effectively. In this solution, the action field naturally relaxes to a state that perfectly cancels the unwanted CP violation, explaining why we don't see its effects and preserving the universe we inhabit. But the story didn't end there. As cosmologists studied this new particle, they realized it had all the right properties to be the mysterious dark matter. An action would be extraordinarily light, potentially billions of times lighter than an electron, and it would be electrically neutral, not interacting via the electromagnetic force at all. Its interactions with normal matter would be incredibly feeble, making it a true ghost particle, streaming through you and the entire Earth as if they weren't even there. And crucially, in the hot, dense early universe, these actions would have been produced in enormous quantities, and their collective mass could easily account for the dark matter that holds galaxies together. The hunt for this cosmic cleaner is now a major frontier in physics, and one of the most sensitive searches is conducted by experiments like ADMX, the Action Dark Matter experiment. The method is as brilliant as it is challenging. It relies on a theoretical prediction that an action in the presence of a very strong magnetic field can convert into a detectable photon. The ADMX apparatus is essentially a super-powered radio receiver inside a massive magnet. Imagine a resonant cavity, a kind of carefully tuned metal chamber, placed inside the bore of a powerful superconducting magnet. The theory goes that if actions are indeed the dark matter, they are everywhere, forming a kind of invisible background ocean throughout our galaxy. As this ocean of actions passes through the experiment's magnetic field, a tiny fraction of them should convert into microwave photons. The trick is that the photon's frequency depends on the action's mass, which we don't know. So the experiment is designed to be tunable, slowly scanning through millions of possible frequencies, listening patiently for a faint, specific signal rising above the background noise. To do this, ADMX must operate at temperatures just a whisker above absolute zero, and use ultra-sensitive quantum amplifiers to hear the faint whisper of a single microwave photon that might be the signature of an action conversion. It is a painstaking process, like searching for one specific grain of sand on all the beaches of the world by slowly sifting through them one scoop at a time. The discovery of the action would be a monumental event, a rare two-for-one triumph for physics. It would simultaneously solve one of the most stubborn puzzles in particle theory, the strong CP problem, and finally reveal the identity of the dark matter that has shaped the cosmos for billions of years. It would show that a single, elegant idea can cleanse our understanding of the subatomic world, while also illuminating the hidden architecture of the universe on its very largest scales. Imagine the universe in its first frantic moments, a seething cauldron of energy and forces undergoing sudden, dramatic shifts. As it expanded and cooled, it went through a series of phase transitions, much like steam condensing into water or water freezing into ice. And just as freezing water can trap bubbles of air or form cracks as it solidifies, the fabric of spacetime itself might have developed its own kind of flaw during these cosmic changes. These hypothetical cracks are known as cosmic strings, not the kind you tie your shoes with, but one-dimensional topological defects, unimaginably thin filaments of pure energy threaded through the cosmos like the cracks in a frozen lake. Their scale is almost impossible to comprehend. A cosmic string would be narrower than a single proton, yet a single meter of it could contain more mass than all of Mount Everest. Stretched across the universe, a single string's total mass could easily exceed that of an entire galaxy, all concentrated into a line so infinitesimally fine it would slice through a planet like a wire cutting through soft cheese. Its gravitational pull so intense it would warp everything in its path. These aren't objects you could hold or see directly. They are more like scars in the geometry of reality, fossil relics from the universe's first moments of existence, when the fundamental forces were still separating from their primordial unity. The concept arises naturally from several grand unified theories, which attempt to describe how the electromagnetic, weak and strong forces were once a single interaction. As the cosmos cooled, the state of this unified field changed, and in the process, it might not have settled perfectly evenly everywhere. In some regions, the field could have gotten stuck in a higher energy configuration, and the boundaries between these different regions would have become trapped as persistent, stable structures, cosmic strings. They are essentially kinks in the field that cannot smooth themselves out, eternal threads woven into the very fabric of spacetime during its birth. If such an entity exists, its presence would be betrayed not by its light but by its gravity. A cosmic string possesses immense mass for its length, and according to general relativity, this would warp the spacetime around it in a profoundly unique way. Because a string is one-dimensional, the curvature it creates is different from the spherical warping of a star or a black hole. Space around a cosmic string becomes conical. A helpful way to picture this is to take a sheet of paper and cut out a thin, pizza slice-shaped wedge. Now, tape the edges of the remaining paper back together. The surface is still flat, but it is now misshapen. If you draw a circle around the point where the tip of the wedge was, you'll find that its circumference is now less than 2 pi times its radius. This is the geometry surrounding a cosmic string, a flat plane with a deficit angle. For an observer, this would create a truly startling optical effect, gravitational lensing of the most perfect kind. Light from a single galaxy directly behind a cosmic string would be bent around both sides of the string. Since the spacetime is conical but otherwise flat, the light rays aren't distorted or smeared, they are simply duplicated. An astronomer looking in the right place could see two identical perfect images of the same galaxy, separated by a small, sharp gap in the sky. This double image signature is one of the most sought-after pieces of evidence for these cosmic scars. Beyond these duplicate galaxies, cosmic strings would also have left their imprint on the oldest light in the universe, the cosmic microwave background. If a string were to move through the primordial plasma at a significant fraction of the speed of light, its intense gravitational field would create a wake, a kind of ripple in the density of matter. As photons from the CMB traveled through this wake, they would gain or lose a tiny amount of energy, an effect known as the Kaiser-Stebbins effect. This would create a very specific, sharp step-like discontinuity in the temperature of the microwave background, a cold spot on one side of the string and a hot spot on the other. While the Planck satellite and other observatories have searched for these telltale steps and thus far found no conclusive evidence, ruling out a large population of strings, the hunt continues for thinner, weaker strings that could still be hiding in the data. The potential existence of cosmic strings connects the most esoteric theories of the universe's birth with observable, astronomical phenomena. They represent a direct link to an era of unimaginable energy, a time when the cosmos was a trillionth of a second old. Finding one would be like discovering the fossil of a creature from the first second of life on Earth. It would provide a tangible, physical window into the processes that shaped everything, confirming that the universe underwent dramatic phase transitions and giving us a new, exotic form of gravitational sculpture in the cosmos. They are a testament to the idea that the earliest moments of creation might have left behind permanent scars, and that the smooth universe we see today could be threaded with invisible, cosmic cracks of unimaginable density. Now, let's turn to a puzzle so fundamental it has eluded scientists for over a century, a phantom particle that would complete one of our most elegant descriptions of nature, the magnetic monopole. Every magnet you have ever encountered, from the one holding a note to your refrigerator to the entire planet Earth itself, is a dipole. It has both a north and a south pole. Cut a standard bar magnet in half and you don't get isolated poles. You simply get two smaller magnets, each with its own north and south. This seems like an unbreakable rule of our universe, but what if it isn't? What if there exists a particle that is a pure north magnetic pole or a pure south, carrying a single, isolated magnetic charge? This hypothetical entity is the magnetic monopole, and its discovery would rewrite textbooks overnight. The case for its existence begins with a beautiful asymmetry in the heart of classical physics. James Clerk Maxwell's equations, formulated in the 19th century, are the majestic set of rules that describe the entire behavior of electricity and magnetism. They are spectacularly successful, predicting everything from radio waves to the nature of light itself. Yet for all their power, they possess a curious aesthetic imbalance. The equations treat electricity and magnetism as two sides of the same coin, but there's a crucial difference. Electric charges exist in isolated units. We have single positive protons and single negative electrons. But for magnetism, the equations contain no such standalone source. Magnetic fields appear only as the result of electric currents or the intrinsic dipole nature of particles. A magnetic monopole would restore perfect symmetry to Maxwell's equations. It would make the electric and magnetic sides of the universe true mathematical equals, allowing for a stunningly symmetric formulation where electric and magnetic charges sit side by side. This isn't just a matter of mathematical elegance, it has a profound physical consequence. The existence of magnetic monopoles would automatically explain a strange and fundamental fact about our world, the quantization of electric charge. Why does every charged particle in the universe have a charge that is an exact integer multiple of the electron's charge? Why is there no particle with, say, 1/3 or 2/7 of that charge? In one elegant sweep, the physicist Paul Dirac showed that if just a single magnetic monopole exists anywhere in the universe, then electric charge must be quantized. The very presence of a magnetic charge would force electric charges to come in discrete, indivisible packets. It's a breathtaking connection, linking the behavior of something as small as an electron to the possible existence of a magnetic particle. But the theoretical appeal of monopoles goes far deeper than classical electrodynamics. They are a direct prediction of many grand unified theories, or GUT. These are the ambitious frameworks that attempt to describe how three of the four fundamental forces, the electromagnetic, weak, and strong forces, were once a single, unified interaction in the extreme energy and temperature of the very early universe. As the cosmos expanded and cooled, this unified force is thought to have undergone a phase transition, much like steam condensing into water, and in the process, it broke into the three distinct forces we see today. These theories suggest that in this cosmic condensation, topological defects would have formed, and one of the most prominent of these defects would be the magnetic monopole. A GUT monopole wouldn't be a simple, tiny magnet. It would be an incredibly massive and exotic object, a stable, solitary magnetic pole that is a relic from the first moments of time, carrying the signature of a unified cosmos within its structure. Its mass would be colossal, potentially as heavy as a bacterium, which for a single subatomic particle is almost unimaginable. This immense mass is the primary reason we haven't stumbled upon one. The energy required to create such a particle is far beyond the reach of any particle accelerator we could ever build. They could only have been forged in the furnace of the Big Bang itself. So where are they? The fact that we don't see them everywhere is actually a major cosmological puzzle in its own right, known as the monopole problem. If GUTs are correct, the early universe should have produced a staggering number of these monopoles, so many that their collective mass would have overwhelmed the cosmos, dramatically altering its evolution and likely preventing galaxies from ever forming. The fact that our universe is not dominated by monopoles was one of the key motivations for the theory of cosmic inflation. That phenomenal, faster-than-light expansion of spacetime would have diluted the density of primordial monopoles to virtually zero within our observable horizon, sweeping them away into the vastness of space beyond what we can see. This means that if they do exist, they are incredibly rare, making the hunt for them a true needle in a cosmic haystack endeavor. For decades, scientists have pursued this phantom with remarkable ingenuity. Early searches involved examining samples of moon rock and ocean floor sediment, on the theory that a heavy, highly penetrating monopole might have gotten trapped there over millions of years. Other experiments have used large loops of wire or induction coils designed to detect the telltale magnetic current that would be generated if a monopole with its powerful magnetic charge were to pass through the loop. Some of the most sensitive searches have been conducted in particle colliders, hoping against the odds to create one in a high-energy collision, and deep underground in the same laboratories that hunt for dark matter, using sophisticated detectors to look for the unique ionization trail a massive, magnetically charged particle would leave behind. Despite these extensive and creative searches, from the depths of old mine shafts to the pristine environment of Antarctic ice, not a single confirmed magnetic monopole has ever been found. Their continued absence is a tantalizing mystery, a ghost in the machine of our most ambitious theories. The discovery of a magnetic monopole would be a scientific event on par with the discovery of the electron or the Higgs boson. It would not only symmetrize our most fundamental equations and explain the quantization of charge, but it would provide the first direct, tangible evidence for grand unified theories and the physics of the universe's first moments. It would be a relic of an era of unity, a frozen-in-time messenger from a period when the forces of nature were one. Until one is found, the monopole remains one of physics' most profound and elegant unfulfilled predictions, a silent testament to the idea that our universe might be more symmetric and more beautifully ordered than the world we currently see suggests. If dark energy is the enigmatic push behind the cosmos and the quantum vacuum is its proposed source, then we must confront the staggering chasm between our theoretical expectations and the reality we observe. This brings us to the very nature of the vacuum itself, not as a void but as the state of lowest possible energy, a simmering foundation upon which all of reality is built. We've touched on the quantum foam, that seething sea of virtual particles, but to grasp the full magnitude of the puzzle, we need to understand the energy this activity implies. Every one of those fleeting particle-antiparticle pairs borrows energy from the universe for its brief existence, and this constant, frantic borrowing and repaying endows every single cubic centimeter of what we call empty space with a fundamental, baseline energy. This is vacuum energy. It's the hum of existence, the cost of doing business in a quantum universe. According to the rules of quantum field theory, we should be able to calculate this energy density by adding up the contributions from every possible frequency of these virtual fluctuations across all the quantum fields that exist. But when physicists perform this calculation, the result is so astronomically large it becomes absurd. The number they arrive at is about 120 orders of magnitude. That's a 1 followed by 120 zeros greater than the value we actually observe for dark energy's density. This isn't just a small rounding error, it is the worst discrepancy between theory and experiment in the entire history of science. To put this number in perspective, it is larger than the number of atoms in the entire observable universe. If the theoretical value were correct, the vacuum energy would have such an immense repulsive gravity that the universe would have been ripped apart in its first instant, before even the simplest atoms could have formed. Stars, galaxies, and life would be impossible. The fact that we exist to ponder this problem tells us that our calculation, while mathematically sound within its own framework, is catastrophically wrong when applied to the cosmos. This yawning gap between prediction and observation is known as the vacuum catastrophe, and it represents a fundamental crisis at the intersection of our two most successful theories, quantum mechanics and general relativity. It screams that we are missing a monumental piece of the puzzle, a deep principle that somehow reconciles the frantic energy of the quantum world with the serene, large-scale behavior of the cosmos. One potential escape route is that some unknown symmetry or cancellation mechanism causes all these enormous positive and negative contributions from different fields to perfectly cancel out, leaving behind only the tiny, residual value we measure as dark energy. Supersymmetry, an elegant theoretical extension of the Standard Model, offered hope for such a perfect cancellation. It predicts that every known particle has a superpartner, and if this symmetry were unbroken, the contributions of these partners to the vacuum energy would indeed cancel out the contributions from the ordinary particles, resulting in a net energy of precisely zero. However, we have not found these superpartners at the energies we've probed, meaning supersymmetry, if it exists, is a broken symmetry. The cancellation is imperfect, and we are still left with a calculated value that is enormous compared to what we see. This leaves physicists with a profoundly unsettling possibility. Perhaps the vacuum energy really is enormous, but its gravitational effect is somehow screened or doesn't couple to gravity in the simple way we assume. Or perhaps our understanding of gravity itself needs a radical revision on cosmological scales. The vacuum catastrophe is not a minor technicality to be brushed aside. It is a glaring signpost pointing toward a future, more complete theory of quantum gravity. It humbles us, reminding us that for all our knowledge, the silent, empty space between the stars holds a secret far deeper than we currently have the tools to understand. Now, as we venture deeper into the quantum world, we encounter a phenomenon where the universe's subtle-handedness manifests in a spectacular way, turning fundamental asymmetries into tangible currents of electricity. This is the chiral magnetic effect, a fascinating process that emerges under the most extreme conditions imaginable, where the distinction between left and right becomes a powerful engine. To understand it, we first need to grasp a property known as chirality. The word comes from the Greek for hand, and just like your left and right hands are mirror images that cannot be perfectly superimposed, some elementary particles possess a kind of handedness. This chirality is related to the direction of a particle's spin relative to its direction of motion. A left-handed particle spins one way as it moves forward, while its right-handed counterpart spins the opposite way. In the familiar, cool universe we inhabit, particles like the electron can flip between these chiral states, and the distinction isn't permanently locked in. But under extraordinary conditions of immense temperature and density, this changes dramatically. Imagine creating a tiny speck of matter so hot and compressed that it melts the very structure of protons and neutrons. This is the state of matter known as quark-gluon plasma, a primordial soup where quarks and gluons, normally locked in confinement, roam freely. This is the environment where the chiral magnetic effect comes to life, and it is recreated regularly in massive particle colliders like the relativistic heavy ion collider at Brookhaven and the Large Hadron Collider at CERN, where scientists smash heavy atoms like gold or lead together at nearly the speed of light. In the fleeting fireball of these collisions, temperatures soar to trillions of degrees, recreating the conditions that existed mere microseconds after the Big Bang. Within this seething plasma, something remarkable can occur. The incredibly powerful magnetic fields generated by the fast-moving, highly charged nuclei involved in the collision can align with the spin of the particles in the plasma. At the same time, the complex and violent interactions can create a local imbalance between the number of left-handed and right-handed quarks. This imbalance, known as a chiral chemical potential, is the first key ingredient. When you have this chirality imbalance present alongside an immensely strong magnetic field, a fascinating quantum process unfolds. The magnetic field affects the left-handed and right-handed particles differently, guiding their motions. This differential effect, combined with the population imbalance, can drive a surge of electric charge, an electric current, to flow along the direction of the magnetic field lines. It's as if the universe's innate preference for one-handedness over the other, when placed in a magnetic crucible, can be harnessed to generate a flow of electricity directly from the quantum properties of the particles themselves. The current generated is not powered by an external battery or a voltage difference in the conventional sense. It is a direct conversion of a quantum topological property into a macroscopic electromagnetic phenomenon. This is not just a theoretical curiosity. Researchers are actively looking for its signature in the data from heavy ion collisions. The telltale sign would be a specific pattern in the particles that fly out from the collision debris. Because the electric current would create a separation of positive and negative charges along the magnetic field's axis, it would lead to a preferential emission of certain charged particles in one direction versus the other, a correlation that stands out against the random background of the explosion. While the evidence is not yet completely conclusive and the signals are subtle, the ongoing hunt is a major effort in nuclear physics. The implications of this effect reach far beyond the laboratory. If it truly occurs, it almost certainly played a role in the universe's infancy. In the first moments after the Big Bang, the entire cosmos was filled with a hot, dense quark-gluon plasma. Immense magnetic fields likely threaded this primordial soup, and the same chiral imbalances could have arisen. This means the chiral magnetic effect may have been a fundamental process in the early universe, generating some of the first electromagnetic currents and potentially seeding the vast magnetic fields that now weave through interstellar and intergalactic space. It represents a beautiful and direct bridge connecting the abstract quantum property of chirality, the colossal force of magnetism, and the generation of a tangible electric current, demonstrating with stunning clarity how the smallest quirks of particle physics can scale up to become cosmic forces in their own right. But for all the power and elegance of the four known forces, a tantalizing question has persisted for decades. What if there are more? We've mapped the cosmic giants and the subatomic architects, but could there be a fifth force, a subtle and secret interaction that has so far escaped our notice? The idea isn't as far-fetched as it might seem. For centuries, we were only aware of gravity and electromagnetism. The strong and weak nuclear forces were completely unknown until the 20th century, hidden within the atom's heart. It is a profound lesson in cosmic humility, suggesting that the forces we take as complete may merely be the most obvious ones. The hunt for a fifth force is a story of tantalizing hints and painstaking precision, a search for a ghost in the machine of the universe. The modern story begins in the 1980s when a team of researchers reanalyzing old experimental data from a mine in Hungary noticed a peculiar anomaly. They were studying the Earth-verse experiment, a classic test of the equivalence principle, the idea that all objects fall at the same rate in a gravitational field, regardless of their mass or composition. The original experiment, performed with incredible care in the early 20th century, used a torsion balance to compare the gravitational attraction of different materials toward the Earth and the Sun. The 1980s reanalysis suggested a tiny, almost imperceptible deviation, a hint that certain materials might experience a minuscule extra force, one that depended on the composition of the object itself. This was shocking, as the equivalence principle is a cornerstone of general relativity. The proposed explanation was a fifth force, a feeble, medium-range interaction that would couple to a property called hypercharge or baryon number, essentially the number of protons and neutrons in an atom. This would mean that a chunk of copper with its specific atomic composition might fall with a subtly different acceleration than a chunk of aluminum if this extra force were present. The physics community was electrified, and a wave of new experiments were launched to test this stunning claim. Researchers descended into deep tunnels to shield their apparatus from seismic noise, used sophisticated pendulums, and built exquisitely sensitive torsion balances. They measured the gravitational attraction between precisely crafted masses in vacuums, looking for any deviation from the perfect inverse square law prediction of Newtonian gravity. The results, however, were a masterclass in how science self-corrects. As measurements became more and more precise, the anomalous signals seen in the reanalyzed data faded away. The consensus today is that those initial hints were likely due to unaccounted for geological or experimental effects. The fifth force in that specific form probably does not exist. Yet the door was not closed, it was merely refined. The hunt had evolved. Today, the search for new forces is more sophisticated than ever, driven by the biggest mysteries we still face: dark matter and dark energy. We know these entities dominate the cosmos, yet we only see their gravitational effects. Could it be that they interact through their own unique forces, a dark electromagnetism, or a long-range dark force that acts only within the hidden sector of the universe? If dark matter particles can interact with each other via a new force carrier, a dark photon or a similar entity, it could explain how they clump together to form the halos that guide galaxy formation. Some of the most intriguing modern experiments are designed to look for just these kinds of interactions. They don't use huge telescopes, they use exquisitely tuned, tabletop apparatuses that can measure forces between minuscule masses with almost unbelievable sensitivity. Imagine two tiny, gold-coated spheres, each smaller than a grain of sand, suspended in a perfect vacuum at temperatures near absolute zero. The experimenters then brings a larger, oscillating mass close by, and they watch the motion of the tiny spheres with lasers. They are measuring the gravitational attraction between these masses with a precision that can detect a force 1,000,000,000 times weaker than the weight of a single bacterium. In this pristine, quiet environment, they are looking for any extra kick on the small spheres, any deviation from the expected gravitational pull that could be the signature of a fifth force coupling ordinary matter to the dark sector. Other searchers look for the potential of this fifth force to cause slight shifts in the energy levels of atoms, or for the spontaneous appearance of dark photons in powerful particle beams. The logic is that if such a force exists, even if it is incredibly weak, the sheer number of particles in an experiment might allow one to momentarily pop into existence, leaving a faint but detectable signal. The pursuit of a fifth force represents a fundamental shift in how we explore the universe. We are no longer just building bigger colliders to smash particles at higher energies. We are also building quieter, more sensitive experiments that can listen for the faintest whispers of new physics. It is a search for the subtlest of melodies in the cosmic symphony, a note so quiet we have not yet learned to hear it, but one that could ultimately reveal the true, full spectrum of forces that weave the fabric of reality. Now we arrive at a force born not from cosmology, but from a deep and subtle imperfection in the mathematical heart of the strong nuclear force, a puzzle whose elegant solution gave us a new field and a prime candidate for the universe's missing matter. This is the Peck-Quinn field, a theoretical entity that exists to solve what physicists call the strong CP problem. To grasp why this problem is so pressing, we need to revisit the strange world of symmetries. We've already seen how the weak force violates CP symmetry, the combination of swapping particles with antiparticles and viewing them in a mirror. This violation is why we live in a matter-dominated cosmos. Yet the strong force which glues quarks together into protons and neutrons presents a mystery. The most successful theory of the strong force, quantum chromodynamics, naturally allows for a term in its equations that would also violate CP symmetry. If this term were present, even at a tiny level, it would have a dramatic and bizarre consequence. It would cause the neutron, which is electrically neutral overall, to possess a tiny electric dipole moment. Imagine the neutron having a slight internal separation of positive and negative charge, like an incredibly minuscule bar magnet but for electricity instead of magnetism. This might sound like an obscure detail, but its implications are cosmic. If this CP violating term existed at the strength the math allows, it would make neutrons behave so differently that the nuclear reactions which forge the elements in stars would fail. The universe as we know it, with its carbon, oxygen, and planets, could not exist. Yet, when physicists perform exquisitely sensitive experiments to measure the neutron's electric dipole moment, they find it to be zero to an astonishing degree of precision. It's as if this troublesome term in the equations has been perfectly cancelled out, tuned to zero with a precision that seems too perfect to be an accident. This is the strong CP problem. Why does the strong force so exquisitely respect a symmetry that it is under no obvious obligation to obey? The brilliant solution proposed by physicists Roberto Peck and Helen Quinn was to introduce a new field that pervades all of space, the Peck-Quinn field. They suggested that this problematic CP violating term isn't a fixed constant of nature, but is instead dynamically cancelled by the state of this new field. Think of it like a universal thermostat for a fundamental asymmetry. the Peck-Quinn field naturally relaxes or adjusts to the specific value that perfectly cancels out the unwanted CP violation, explaining why we never see its effects. It's a beautifully elegant mechanism that cleans up the equations and preserves the universe we observe. But the story didn't end with cleaning up a particle physics puzzle. Soon after, physicists Frank Wilczek and Steven Weinberg realized that this elegant solution had a spectacular physical consequence. Just as ripples in the Higgs field manifest as the Higgs boson, ripples in the Peck-Quinn field would manifest as a new, very light particle. Wilczek named it the action after a brand of laundry detergent because it cleaned up the strong CP problem so effectively. This is a stunning connection. A field invented to solve an abstract issue in nuclear physics spontaneously gives rise to a new particle. And as cosmologists studied this proposed action, they had a revelation. This particle had all the right properties to be the mysterious dark matter. It would be electrically neutral, incredibly light, potentially billions of times lighter than an electron, and would interact with normal matter only with the feeblest of forces, passing through the entire Earth as if it weren't there. Most importantly, in the hot, dense early universe, these actions would have been produced in colossal numbers, and their collective mass could easily account for the invisible gravitational scaffolding that holds galaxies together. This creates a breathtakingly elegant bridge between two of physics' greatest mysteries. The Peck-Quinn field, by solving the strong CP problem in the subatomic world, simultaneously provides a compelling candidate for the dark matter that dominates the cosmos on the largest scales. It shows how a single, unseen force can provide a unified solution, connecting the quantum rules that govern atomic nuclei with the gravitational architecture of the universe itself. The hunt for the action is now a major experimental endeavor, with projects like the Action Dark Matter experiment using powerful magnets and ultra-sensitive detectors to listen for the faint whisper of this particle converting into a microwave photon. Discovering it would be a monumental two-for-one triumph, validating a clever solution to a decades-old particle theory puzzle, while finally illuminating the identity of the invisible matter that shapes the cosmic web. Now, let's explore a cosmic phenomenon that acts as a permanent measuring tape stretched across the heavens, a frozen echo from the universe's infancy that allows us to trace the influence of dark energy with breathtaking precision. These are Barrian acoustic oscillations. To understand them, we have to journey back to the first 400,000 years after the Big Bang, when the cosmos was not transparent and dark, but a brilliant, seething fog of plasma. In this primordial soup, ordinary matter, primarily protons and electrons, collectively known as baryons, was entangled with an intense bath of light, the photons. This hot, dense plasma was a turbulent arena where two fundamental forces were locked in a constant tug of war. On one side, gravity was tirelessly at work, trying to pull the baryons inward to collapse them into denser clumps. Pushing back with immense power was the pressure from the radiation, the relentless torrent of photons that acted like a fierce wind, preventing the matter from collapsing. This struggle between gravitational collapse and radiation pressure set the entire universe ringing like a bell, generating colossal spherical sound waves that raced outward through the plasma at a significant fraction of the speed of light. These weren't sound waves as we hear them, but rather coherent, rhythmic compressions and rarefactions, regions of slightly higher and lower density expanding through the early cosmos. For nearly 400,000 years, these waves propagated, with the photon pressure acting as the restoring force, much like the springiness of air that allows sound to travel. The leading edge of each wave, a shell of compressed matter and radiation, continued to expand. Then, a pivotal event occurred, one we've touched on before: recombination. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. In an instant, the fog cleared. The photons, which had been constantly scattering off the free electrons, were suddenly set free. This is the moment the cosmic microwave background was released, that snapshot of the infant universe. But something else happened at that exact moment that would leave a permanent imprint on the cosmos. When the photons decoupled from the matter, the radiation pressure that had been driving the sound waves vanished. The waves instantly froze in place. Imagine a circular ripple expanding across a pond, and at the very moment it reaches its maximum size, the entire pond suddenly turns to solid ice, preserving that ripple forever. This is exactly what happened throughout the entire universe. Every initial overdensity, every seed from which a galaxy cluster would eventually grow, became surrounded by a single, fossilized spherical shell of matter. This shell marked the maximum distance that a sound wave could have traveled from that central point in the time before recombination. This distance became a fundamental, fixed scale in the cosmos. Over the ensuing billions of years, gravity continued to work, pulling matter into the dense central regions to form galaxies and galaxy clusters, but it also pulled matter inward from that fossilized shell. The result is a subtle but powerful statistical pattern woven into the large-scale structure of the universe. If you could take a census of the positions of millions of galaxies, you would find a slight but definitive preference for pairs of galaxies to be separated by a specific distance, the radius of that ancient sound wave. It's as if the cosmos has a built-in ruler, and all the structures we see are subtly aligned to its markings. So what is the length of this cosmic ruler? The frozen sound horizon measures about 500 million light-years across. This is not a random number. It is a direct consequence of the speed of sound in the primordial plasma and the age of the universe at recombination. It is a standard ruler whose true physical size we can calculate with great accuracy from our understanding of the early universe. This is what makes baryon acoustic oscillations one of the most powerful tools in modern cosmology. By observing how this fixed scale appears to us at different distances, and therefore at different epochs in cosmic history, we can measure the expansion of the universe with phenomenal precision. When we look at galaxies that are, say, 5 billion light-years away, we are seeing them as they were 5 billion years ago. We can measure the apparent angular size of the baryon acoustic oscillation peak in that epoch. By comparing that apparent size to the known true size of the ruler, we can calculate the distance to those galaxies and thus determine how much the universe has expanded over that 5 billion-year interval. We can do this for galaxies at various distances, effectively charting the expansion history of the cosmos. This is precisely how baryon acoustic oscillations are used to probe the nature of dark energy. In a universe dominated by matter, the expansion rate slows down over time. But if dark energy is causing the expansion to accelerate, then the relationship between distance and the apparent size of the baryon acoustic oscillation scale will be different. By meticulously mapping the three-dimensional positions of countless galaxies in immense sky surveys projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, scientists have constructed a cosmic map of unprecedented detail. They can see the faint, whispery imprint of these ancient sound waves at different slices of cosmic time. The data reveals the subtle shift in the expansion rate, confirming the acceleration and tightly constraining the properties and equation of state of dark energy. It provides an independent and powerful confirmation of the findings from supernova, cementing our picture of a cosmos driven by an unseen, repulsive force. This incredible technique allows us to use the faint, frozen music of the Big Bang as a precise gauge to measure the very fabric of spacetime itself, turning the subtle statistical clustering of galaxies into one of the most reliable guides to the ultimate fate of our universe. Now, let's turn our attention to a subtle but profound imprint on the oldest light we can see, a feature that reveals not just the state of the infant universe, but our own motion through the vast cosmic expanse. This is the cosmic microwave background dipole, and it serves as a celestial speedometer for our entire solar system. The cosmic microwave background radiation is famously uniform, a near-perfect blackbody glow that fills every direction of the sky with a temperature of just 2.725 degrees above absolute zero. But when scientists began making ever more precise measurements of this relic heat, they discovered a tiny, consistent asymmetry. One hemisphere of the sky, centered roughly in the direction of the constellation Leo, is ever so slightly warmer, while the opposite hemisphere, centered near Aquarius, is correspondingly cooler. The difference is minuscule, only about 0.003 of a degree, but it is unmistakable and fundamental. The most compelling explanation for this dipole anisotropy is a phenomenon we experience with sound here on Earth, the Doppler effect. Just as the pitch of a siren seems to rise as an ambulance races toward you and fall as it speeds away, light waves are also affected by relative motion. If you are moving toward a source of light, its waves are compressed, shifting them to a higher frequency and making the light appear slightly bluer and more energetic, which for the microwave background translates to a slightly higher temperature. When you are moving away from the light source, the waves are stretched, shifting them to a lower frequency, making the light redder and cooler. The entire cosmic microwave background serves as the ultimate stationary reference frame, the rest frame of the cosmos as a whole, set when the radiation was first released. Our solar system is not sitting still relative to this primordial backdrop. We are on the move, and as we hurtle through space, we are effectively running into the microwave photons in the direction we're heading, warming them up while fleeing from the photons behind us, cooling them down. By carefully analyzing the precise amount of this temperature shift, astronomers can calculate our velocity with extraordinary precision. The result is a staggering cosmic velocity. Our entire local group of galaxies, including the Milky Way, is moving at approximately 630 kilometers per second. That's over 1.3 million miles per hour relative to the rest frame of the cosmic microwave background. This isn't just the Sun orbiting the galaxy. This is the combined motion of our Sun, the galaxy's rotation, and the entire Milky Way being pulled through the universe. Our ultimate destination in this grand voyage is a point in the sky known as the Great Attractor, a massive gravitational anomaly located in the general direction of the Centaurus constellation. This region, which includes the immense Norma cluster and the central concentration of the Laniakea supercluster, is pulling us, along with thousands of other galaxies, toward its immense gravitational well. The cosmic microwave background dipole is therefore so much more than a minor temperature variation. It is our proof that we are not privileged stationary observers. We are participants in a dynamic, flowing cosmos, riding a galactic carousel while simultaneously being swept along a river of gravity on a scale almost too large to comprehend. It provides a fixed coordinate system against which all other motions in the universe can be measured, a cosmic cornerstone that grounds our understanding of velocity and direction in the vast, expanding tapestry of space. That sense of motion we feel from the cosmic microwave background dipole isn't just an abstract measurement. It points us toward a specific, colossal destination, a gravitational focal point that has captivated astronomers for decades, known as the Great Attractor. For a long time, this was one of the most profound, X marks the spot mysteries in all of cosmology. We knew we were being pulled, we could measure our speed with incredible accuracy, but when we looked in the direction we were heading, our view was blocked. The culprit is our own galaxy. The plane of the Milky Way is thick with gas, dust, and countless stars, creating a dusty band across the sky that obscures our vision of the distant universe beyond. Astronomers call this the zone of avoidance, and it effectively rendered a huge swath of the cosmos behind it a blind spot, a place where the Great Attractor was suspected to lurk, hidden from our optical and even many of our early radio telescopes. It was a truly unsettling idea, a ghost in the intergalactic darkness, an unseen mammoth of mass tugging at our entire galactic neighborhood without revealing itself. As observational technology advanced, particularly with satellites equipped with infrared and X-ray eyes that could peer through the galactic smog, the veil began to lift. What we found was not a single monstrous object, but something both more complex and more in line with our understanding of cosmic structure. The Great Attractor is now understood to be the gravitational core of our local supercluster, which we now call Laniakea, a Hawaiian word meaning immense heavens. This is not a single galaxy or a lone, supermassive black hole, but the central gravitational basin of a vast collection of matter. Imagine a continent of galaxies, with the Great Attractor representing its most massive and dense mountain range. This region, centered on the Norma cluster, is an immense confluence of galaxies and dark matter, a gravitational anchor point for our entire local volume of space, including the Milky Way, Andromeda, and tens of thousands of other galaxies. Its pull is the dominant force organizing the motion of galaxies across hundreds of millions of light-years. Yet, solving one mystery often reveals a deeper one. As we mapped the peculiar velocities of galaxies, that is, their motions over and above the general expansion of the universe, we discovered something even more staggering. The pull of the Great Attractor alone couldn't account for the full scale and speed of the flow we are part of. Our journey doesn't end there. It seems our entire local universe, including the Great Attractor itself, is caught in an even grander river of motion, all streaming toward something far more massive and distant. This ultimate destination is known as the Shapley Attractor, the largest concentration of mass in our observable cosmic neighborhood. Located over 600 million light-years away in the constellation of Centaurus, the Shapley supercluster is a staggering assemblage of dozens of rich galaxy clusters, a veritable metropolis of galaxies and the dark matter that binds them. Its gravitational influence is so immense that it dominates the motion of galaxies across nearly 1 billion light-years. So the picture that emerges is one of a cosmic hierarchy of pulls. Our Milky Way is gravitationally bound to the local group, which is in turn falling toward the core of the Virgo cluster. But all of that is merely part of a larger cascade into the Great Attractor basin. And that entire flow, the Great Attractor and all its celestial subjects, is itself just a tributary in a far vaster cosmic river, all being drawn inexorably toward the gravitational behemoth that is the Shapley supercluster. This grand narrative of nested attractions reveals the true power of dark matter on the largest scales. It is the unseen skeleton of this entire structure, its gravity shaping these immense flows and directing the motion of the luminous galaxies we can see. The journey from a mysterious temperature fluctuation in the cosmic microwave background to the discovery of our place within this immense cosmic watershed shows how we are not just observers of the universe, but active participants in a dynamic, gravitational dance on the very grandest of stages. But while we often look to the cosmos for its grand natural mysteries, one of the most pressing dangers to our future in space is an unseen force of our own creation, a potential catastrophe lurking just a few hundred miles above our heads. This is the Kessler syndrome, a chain reaction of destruction that could, in effect, place an invisible shield around our planet, one made not of energy but of shrapnel. The scenario, first detailed by NASA scientist Donald Kessler in 1978, begins with the ever-growing cloud of debris we have placed into low Earth orbit. Think of this region not as a vast, empty void, but as a celestial highway buzzing with activity. There are active satellites providing everything from GPS and weather forecasting to global communications and scientific data. But sharing this space is a population of ghost defunct satellites, spent rocket boosters, and millions of tiny fragments from past explosions and collisions. This is the orbital debris environment, and it is getting more crowded every year. The Kessler syndrome describes the tipping point where the density of objects in a particular orbital band becomes so high that a single collision is statistically unavoidable. When that first major collision occurs, say between an old, derelict satellite and a discarded rocket body, it doesn't just create two new pieces of debris. It creates thousands. The energy involved in such a high-speed impact with closing velocities of up to 36,000 kilometers per hour is staggering. A collision turns two large objects into a swirling cloud of shrapnel-jagged fragments ranging in size from a bus down to a screw. Each one of these new fragments is now an unguided projectile, carrying enough kinetic energy to obliterate any satellite or spacecraft it encounters. And that is where the cascade begins. Each new piece of debris vastly increases the probability of the next collision. One impact becomes 2, then 4, then 8, in a rapidly escalating, self-sustaining chain reaction. The debris cloud expands, a shrapnel storm spreading through the orbital highway. As the cascade progresses, the entire orbital region could become so saturated with lethal fragments that it is rendered completely impassable and unusable. The terrifying reality of this syndrome is its longevity. In the vacuum of space, there is no air resistance to slow these fragments down. Objects in low Earth orbit do experience a tiny amount of drag from the wisps of the upper atmosphere, but for most debris, this process is achingly slow. A piece of debris generated in a collision at an altitude of 800 kilometers could remain in orbit for decades or even centuries. This means that a single, catastrophic cascade event could effectively lock humanity out of a significant portion of near-Earth space for generations. The immediate consequences would be devastating for our modern, connected world. Our global fleet of satellites would be systematically destroyed. We would lose GPS navigation, crippling shipping, aviation, and financial networks that rely on precise timing. Weather forecasting would revert to 1970s level accuracy, leaving populations vulnerable to severe storms. Global communications and internet services provided by satellite constellations would fail. The International Space Station, a symbol of international cooperation, would be under constant mortal threat, its armored hull potentially unable to withstand a hit from a larger fragment, forcing its evacuation and abandonment. But the longer-term consequence is even more profound. A full-blown Kessler syndrome event in low Earth orbit would trap us on our planet. Launching any new spacecraft through that shell of whirling debris would be like trying to drive a car through a shotgun blast. The windows for safe launch would vanish and the risks would become unacceptably high. Dreams of returning to the Moon, missions to Mars, and the broader expansion of humanity into the solar system would be put on hold, possibly for centuries, until the debris cloud slowly, naturally decayed. This is not a distant science fiction threat. We have already had frightening previews. In 2009, a defunct Russian communications satellite, Cosmos 2251, collided with an active American commercial satellite, Iridium 33. The event created over 2,000 large, trackable pieces of debris and countless smaller ones, all of which join the catalog of objects that spacecraft must now regularly maneuver to avoid. Then, in 2007, China intentionally destroyed one of its own aging weather satellites in an anti-satellite missile test, an act that single-handedly created the largest debris cloud in history, with over 3,000 trackable objects that continue to threaten other satellites today. Every time two objects collide or one is deliberately destroyed, we take a step closer to that critical density threshold. The problem is compounded by the rise of massive commercial satellite constellations involving tens of thousands of individual satellites. While these promise global internet coverage, they also dramatically increase the traffic in already crowded orbits, raising the stakes for collision avoidance and the potential scale of a cascade if control is ever lost. The effort to combat this invisible, human-made force is a race against time. Space agencies around the world continuously track over 30,000 objects larger than a softball, but millions of smaller, untrackable fragments are just as lethal. Satellite operators are now required to have plans to deorbit their spacecraft at the end of their lives, either by guiding them to burn up in the atmosphere or moving them to a graveyard orbit. Researchers are also developing active debris removal technologies, concepts involving nets, harpoons, robotic arms, and even lasers to nudge debris toward atmospheric re-entry. The Kessler syndrome is a stark reminder that the greatest threats can sometimes emerge from our own progress. It is an unseen force born from neglect, a cascade of consequences that could literally enclose our world in a cage of our own making, reminding us that the freedom to explore the cosmos is a fragile privilege that requires constant, vigilant stewardship. Now, let's explore a subtle yet profound effect predicted by Einstein's theory, one that reveals how mass doesn't just warp space but also twirls it like a spoon stirring honey. This is frame dragging, a phenomenon where a massive rotating object literally pulls the fabric of spacetime around with it as it spins. To visualize this, picture a perfectly smooth, tranquil pond representing the fabric of spacetime. Now imagine placing a small, stationary ball in the center of the pond. The water's surface dips downward, creating a gentle curve. This is the standard curvature of gravity we're familiar with. But now, set that ball spinning rapidly. If the pond were filled with a thick, viscous fluid like honey, the spinning ball wouldn't just sit there. It would drag the surrounding honey into a circular motion around itself. The fluid closest to the ball would move the fastest, creating a whirlpool effect that gradually diminishes with distance. In this analogy, the honey is space-time itself, and the spinning ball is a rotating planet or star. The theory of general relativity tells us that any rotating mass generates this effect, technically known as the lens-Thirring effect. It means that space and time are not just a passive stage. They are a dynamic, malleable medium that can be set into motion by the objects within it. The closer you are to the rotating body, the more you are caught in this invisible, cosmic whirlpool, forced to move along with the twisted contours of space-time. Proving this extraordinary prediction required one of the most precise and patient experiments in the history of science, the Gravity Probe B mission. Conceived in the 1960s and finally launched in 2004, this NASA mission was a technological marvel. At its heart were 4 of the most perfect gyroscopes ever created, spheres of fused quartz so spherical and uniform that they were described as the roundest objects ever made by humans. These gyroscopes were housed in a satellite orbiting Earth in a perfect polar orbit, and they were kept spinning and isolated from any external disturbance at a temperature near absolute zero. The concept was brilliantly simple, yet its execution was fiendishly difficult. According to Newtonian physics, the spin axes of these perfect gyroscopes should have remained fixed forever, pointing at a distant guide star as a constant reference. But general relativity predicted 2 tiny changes due to Earth's presence. One was the geodetic effect, a warping of space due to Earth's mass, and the other was the far smaller frame dragging effect caused by Earth's rotation. Over the course of a year, Gravity Probe B's exquisitely sensitive instruments measured the minuscule drift in the gyroscope's alignment. The result, announced after years of painstaking data analysis, was a triumphant confirmation. The gyroscopes had indeed been dragged ever so slightly by the spinning Earth. The measured shift was tiny, a drift of just 39 milliarcseconds per year. To grasp that scale, it's like measuring the thickness of a sheet of paper from over 100 miles away. This successful detection was a direct validation that our planet, simply by spinning, twists the very coordinates of reality around it. While the effect is almost imperceptible around Earth, its power becomes truly cosmic around the most extreme objects in the universe, rotating black holes known as Kerr black holes. Around a stationary black hole, there's a point of no return called the event horizon. But around a spinning Kerr black hole, frame dragging becomes so intense that it creates a region outside the event horizon called the ergosphere. Within this warped, pumpkin-shaped region, spacetime itself is being dragged around the black hole at velocities approaching the speed of light. The effect is so powerful that it becomes impossible for any object, even light, to remain stationary. Everything is forced to co-rotate with the black hole's ferocious spin. This has dramatic consequences for the environment around these gravitational monsters. Most stellar mass black holes are part of binary systems, and they pull gas from a companion star. This gas doesn't fall straight in. It forms a flattened, swirling structure called an accretion disk. The intense frame dragging near a Kerr black hole governs the dynamics of this entire disk. It imparts additional energy and angular momentum to the innermost orbits, influencing how fast material can spiral inward and ultimately how much energy is released as brilliant X-rays and gamma rays before the material crosses the event horizon. In fact, the rotation of a supermassive black hole, powered by frame dragging, is thought to be the engine behind the relativistic jets that shoot out from the cores of active galaxies, beams of energy so powerful they can be seen across the universe. Frame dragging is not just a curious footnote in Einstein's theory. It is a fundamental property of our dynamic universe, a testament to the fact that mass tells spacetime how to curve and motion tells spacetime how to twist. It connects the delicate, precise measurement of a gyroscope in Earth orbit to the violent, energetic whirlpools around cosmic giants, showing us that even the void of space is never truly still. After exploring the invisible walls of Kessler syndrome and the twisting of spacetime itself, we arrive at a concept that shifts our perspective from the forces that govern the cosmos to the very fact that we are here to observe them. This is the anthropic principle, a powerful and often controversial idea that stands at the crossroads of physics, philosophy, and cosmology. It begins with a simple yet profound observation. The fundamental constants of our universe appear to be exquisitely fine-tuned for the existence of life. Consider the strength of gravity, the mass of an electron, or the value of the fine structure constant that dictates the power of electromagnetism. If any of these were altered by even a tiny percentage, the universe would be utterly sterile. A slightly stronger gravitational constant, and stars would burn through their fuel in millions of years instead of billions, not leaving enough time for planets to form and life to evolve. A slightly different value for the strong nuclear force and carbon. The fundamental building block of life as we know it might never be forged in the hearts of stars. The list of these cosmic coincidences is long and deeply compelling, suggesting a universe that seems almost designed for our presence. The anthropic principle offers a powerful, if humbling, explanation for this apparent fine-tuning. In its simplest form, the weak anthropic principle states that we should not be surprised to find the constants of nature set to values that allow our existence, because if they were any different, we simply wouldn't be here to notice. It is a cosmic version of the observation that a fish lives in water because if it lived on land, it would be a different kind of creature entirely. Our observations of the universe are necessarily filtered by the requirement that those observations require an observer. We are not looking at a random universe. We are looking at a universe that has the specific properties needed to produce us. This shifts the question from why is the universe so perfectly suited for life to what must the universe be like for life to exist within it. The principle becomes a vital tool for reasoning, helping physicists discard theories that would lead to a universe incapable of supporting conscious observers. Then there is the more radical strong anthropic principle, which posits that the universe must have properties that allow life to develop within it at some stage in its history. This version edges into more philosophical territory, sometimes interpreted to mean that the existence of observers is a necessary component of the cosmos, almost as if the universe knows we are here. While this stronger interpretation is far more speculative and less widely accepted in scientific circles, it highlights the deep mystery of why a universe with such specific, life-permitting rules should exist at all. This line of thinking finds a powerful and perhaps the most compelling resolution in the concept of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of universes, each with its own unique, randomly determined set of physical laws and constants, then the mystery of fine-tuning evaporates. In this cosmic landscape, sometimes called the cosmic archipelago, most universes would be stillborn or barren. Some might expand too rapidly for galaxies to form, others might have forces too weak to bind atoms, and still others might collapse back on themselves instantly. We, of course, find ourselves not in a typical universe, but in one of the incredibly rare, finely tuned ones where the numbers just happen to come out right for stars, planets, and eventually life to emerge. There was no designer and no grand plan, just the inevitable statistical outcome of a vast enough ensemble of possibilities. In this multiverse picture, the anthropic principle becomes a straightforward selection effect. We are not a special product of a special universe. We are simply the inhabitants of one of the few habitable neighborhoods in a much grander reality. This idea is supported by certain interpretations of cosmic inflation, which suggest that once inflation begins, it can be eternal, continually spawning new pocket universes with different physical properties. The discovery of dark energy and its peculiarly small value, a central part of the cosmological constant problem, is often cited as potential evidence for this anthropic reasoning. Perhaps the value we measure isn't fundamental, but is simply the value that, by chance, ended up in our particular pocket universe, allowing galaxies to form and life to arise. While the anthropic principle and the multiverse offer a breathtakingly vast perspective, they are not without their critics. Some argue that invoking an unobservable multiverse to explain the features of our own universe is a form of philosophical surrender, a way of avoiding the search for a deeper, more fundamental theory that could explain why our constants have the values they do from first principles. Others point out that we do not yet know how wide the range of life-permitting constants truly is. Perhaps life could exist in forms we cannot even imagine under vastly different physical laws, making our universe less special than it appears. Ultimately, the anthropic principle forces a profound shift in our cosmic self-image. It challenges the Copernican principle that we occupy no special place in space, suggesting instead that while our location may be ordinary, our time in cosmic history and the very laws we observe might be incredibly special. It connects our existence as conscious beings directly to the most fundamental workings of reality, suggesting that the universe is not just a collection of impersonal forces, but a stage upon which the emergence of observers is an integral and perhaps inevitable part of the story. But to truly stretch the limits of what reality might be, we must now confront one of the most radical ideas to emerge from theoretical physics, a concept that turns our entire perception of the universe inside out. This is the holographic principle. The story of this astonishing idea begins not with the cosmos at large, but with the most information-dense objects we know of, black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal, building on the work of Stephen Hawking. He argued that a black hole's entropy, which is a measure of the disorder, or more profoundly, the information content of a system, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon. This was a profound clue. In ordinary systems, like a box of gas, the more space you have, the more different ways you can arrange the molecules inside, and thus the higher the entropy. But for a black hole, the ultimate container, the maximum amount of information it can hold is dictated not by the volume it encloses, but by the two-dimensional area of its boundary. It's as if all the data about what fell into the black hole, every star, every planet, every atom, is not stored in the vast, dark interior, but is somehow encoded on the surface of its point of no return, like a cosmic hard drive with information painted onto its shell. This bizarre finding was the first hint that the universe might operate on a holographic basis. The principle was later solidified by work in string theory, most notably by Leonard Susskind and Gerard T. Hooft. They proposed that this isn't just a quirky property of black holes, it could be a fundamental law of the universe. The holographic principle asserts that all the information needed to describe a volume of space can be thought of as residing on its lower dimensional boundary. To grasp this, think of an ordinary security hologram on your credit card. The flat, two-dimensional plastic surface, when illuminated with light, projects a full three-dimensional image that you can look around. The holographic principle suggests that our entire universe, with its three spatial dimensions of length, width, and height, might be a similar kind of projection. The data required to generate everything we see and experience, every galaxy, every person, every thought, could be stored on a vast, distant, two-dimensional surface that surrounds us, a cosmic film at the edge of the observable universe. In this breathtaking view, the world we perceive as solid and three-dimensional is a magnificent illusion, a holographic translation of information stored on a flat surface. This completely upends our classical notions of locality, the idea that objects and events exist at specific points in space. In a holographic universe, what happens here in this room is intimately connected to the data being processed on that far-off boundary. A particle's position in three-dimensional space isn't its fundamental reality. It's an emergent property decoded from the information on the two-dimensional screen. This also provides a tantalizing path toward solving the greatest problem in theoretical physics, unifying gravity with quantum mechanics. The problem has always been that gravity, described by the smooth geometry of spacetime in general relativity, seems fundamentally incompatible with the frantic, discrete quantum world. But in the holographic framework, a powerful duality emerges. Certain theories of a gravitational universe, like one with a type of anti-de Sitter space, can be exactly equivalent to a quantum field theory without gravity operating on its lower dimensional boundary. This is the famous AD/S/CFT correspondence. It means that a problem that is impossibly difficult to solve in the gravitational, three-dimensional world can be translated into a different but equivalent problem in a quantum theory on the two-dimensional boundary, where it might be much easier to solve. Gravity and our three-dimensional reality are not the primary truths. They are a grand, emergent consequence of a quantum system playing out on a distant, flat canvas. While the exact mathematical correspondence is best understood in these specific, hypothetical universes, the principle inspires a radical rethinking of our own cosmos. If true, it would mean that the fundamental building blocks of reality are not tiny, zero-dimensional points or vibrating strings, but bits of information, ones and zeros, written on the fabric of spacetime at its ultimate scale. The universe would be, at its heart, a vast cosmic computation, and we are the magnificent dynamic output of that calculation, living in a reality that is both stunningly real and at the same time the ultimate illusion. And so we arrive at the final and perhaps most expansive, unseen force shaping not just our universe, but the very possibility of reality itself, the multiverse. This is the ultimate unseen realm, the grand stage upon which our own cosmos might be just one performance among an infinite number. The idea is deceptively simple. What we call the universe, everything we can possibly observe from the Big Bang to the farthest galaxy, may be merely a single bubble in a vast, frothing cosmic ocean, a single page in an infinite book of physical laws. This is not merely science fiction. It emerges as a potential, and in some cases unavoidable, consequence of our most sophisticated theories about cosmic inflation, string theory, and quantum mechanics. The first, and perhaps most well-supported, version is the inflationary multiverse. We've already discussed how a runaway inflated field could have blown up a tiny patch of space into our entire observable cosmos. But many models suggest this inflation is not a one-time event. Instead, it could be eternal. picture a vast, unstable energy landscape, a cosmic mountain range. Our universe formed when one specific inflattened field rolled down one specific hill, but the theory suggests that in the broader meta realm, this process never stops. Quantum fluctuations continuously cause new patches of spacetime to erupt into their own inflationary expansions, each one giving birth to a new, self-contained bubble universe. In this eternal inflation scenario, the cosmos is a bubbling cauldron, constantly spawning new universes, each with its own Big Bang and its own subsequent history. Our entire reality is just one bubble among countless others in an ever-growing multiverse foam. Then there is the multiverse predicted by string theory, often called the string theory landscape. String theory, a leading candidate for a theory of everything, suggests that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. The way these strings vibrate determines the properties of the particles we see, like an electron or a quark. However, for the theory to be mathematically consistent, it requires extra spatial dimensions beyond the 3 we experience, often 6 or 7 more, all curled up into a complex microscopic shape. The problem and the source of the multiverse is that string theory allows for a staggering number of possible ways for these extra dimensions to curl up, perhaps 10 to the power of 500 different configurations. Each distinct configuration results in a universe with different effective laws of physics and different values for its fundamental constants, like the strength of gravity or the mass of the electron. This vast landscape of possibilities means that if string theory is correct, a multiverse isn't just likely, it's a mathematical inevitability. Our universe, then, is simply one point in this unimaginably vast landscape, one particular solution where the numbers happen to work out in a way that allows for our existence. Perhaps the most mind-bending version of all comes not from cosmology, but from the quantum realm, the many worlds interpretation. Formulated by Hugh Everett in the 1950s, this interpretation takes the quantum wave function, which describes all the possible states of a particle utterly seriously. It proposes that every time a quantum event occurs with multiple possible outcomes, the universe doesn't randomly select one outcome. Instead, it splits or branches into multiple copies, one for each possibility. In one universe, the radioactive atom decays. In another, identical in every other way, it does not. In one universe, you turned left on your way to work. In another, you turned right. This branching happens constantly at every quantum juncture, creating a near-infinite tree of parallel realities. In this view, the multiverse is not a collection of distant, disconnected bubbles, but an ever-branching, ever-diverging tapestry of alternate histories and futures, all equally real, all unfolding simultaneously. So, what would these other universes be like? The possibilities are as boundless as the multiverse itself. In some bubble universes, the strength of the weak nuclear force might be slightly stronger, meaning hydrogen would fuse into helium so rapidly in the early universe that no stars could form, leaving a dark, empty cosmos. In others, the cosmological constant might be immensely powerful, ripping space-time apart in a violent, big rip before the first atoms could even coalesce. There could be universes with 4 fundamental forces or only 2. Universes where the proton is unstable and matter instantly evaporates, or universes where dark matter doesn't exist and galaxies never take shape. In the quantum many worlds, there are realities where every possible outcome of every quantum event is realized, worlds where dinosaurs never went extinct, where life evolved on Mars, or where you made a different choice at every pivotal moment in your life. While the concept is staggering, the most pressing scientific question is, can we test it? Currently, the direct detection of another universe seems impossible by definition. They exist beyond our cosmological horizon, in domains of space-time from which no signal, not even light, can ever reach us. However, scientists are exploring indirect methods. If our bubble universe collided with another in the distant past, the immense energy of that impact could have left a specific, circular pattern in the cosmic microwave background, a cosmic bruise that we might one day detect. Alternatively, if the fundamental constants of nature aren't truly constant, but vary slightly across the wider multiverse, we might find subtle variations in these constants in different parts of our own sky. The most profound implication of the multiverse, however, lies in its potential to solve the ultimate why question, the problem of fine-tuning. As we've seen throughout this journey, our universe's constants appear meticulously calibrated for life. If the strong force were just 2% stronger, diprotons would be stable and stars would burn their fuel in mere millions of years. If the electromagnetic force were a few percent weaker, no atoms besides hydrogen would be possible. This incredible precision has led some to propose a divine designer. The multiverse offers a powerful, naturalistic alternative, the anthropic principle. In an infinite or near-infinite ensemble of universes with physical laws set at random, it is statistically inevitable that a tiny, tiny fraction will, purely by chance, have the right combination of constants to allow for stars, planets, and life. We, of course, can only find ourselves in one of those rare, habitable universes. Our existence is therefore not a miracle, but a selection effect. We are the universe that won the cosmic lottery, and we shouldn't be surprised to find ourselves in a place that can support us. The multiverse remains the most controversial of all the unseen forces. For some, it is a logical and compelling extension of our best theories, a necessary consequence of inflation, quantum mechanics, and string theory. For others, it is an untestable, metaphysical concept that lies outside the bounds of science, a theory that can explain anything and therefore predicts nothing. Yet it represents the ultimate frontier of human curiosity, the final, humbling step in a long journey of cosmic demotion. We once thought Earth was the center of creation, then our sun, then our galaxy. Now, the multiverse suggests that even our entire cosmos, with its hundreds of billions of galaxies, may be an insignificant speck in a far grander reality. It challenges our very definition of what is real and forces us to confront the possibility that all that we see and know is just one tiny, shining fragment of an infinite and eternal whole. And so we reach the end of our journey, a voyage that has taken us from the largest cosmic structures down to the very foam of spacetime, guided by the silent, invisible hands that truly govern existence. We have met the dark titan's dark matter, whose gravitational scaffold allows galaxies to spin without flying apart, and dark energy, that mysterious repulsive force accelerating the expansion of the cosmos, pulling the universe toward a cold, isolated future. We have explored the quantum realm, where fields and fluctuations are the true bedrock of reality, where the Higgs field gives particles their substance and the inflatoned field set the entire cosmic story in motion. We have witnessed how the curvature of spacetime itself is the true nature of gravity, how the strong and weak nuclear forces build and transform the elements of life, and how entanglement weaves a web of instantaneous connection that defies our classical intuition. We have ventured to the edges of theory, contemplating torsion fields, cosmic strings, and the holographic principle, ideas that stretch our understanding of what is possible. We have even confronted the shadow of our own presence in the Kessler syndrome and the philosophical implications of the anthropic principle. Through it all, one profound truth emerges: the universe we see with our eyes and telescopes, the glittering stars, the majestic galaxies, the planets and moons, is just the faintest shimmer on the surface of a profoundly deeper reality. These 30 unseen forces are not minor players. They are the directors, the choreographers, and the architects of everything. They determine the fate of galaxy clusters, the stability of atoms, the very possibility of consciousness. The visible matter that makes up our world accounts for less than 5% of the cosmos. The rest is this dark, unseen symphony of influences. This journey should leave us with a powerful sense of humility and wonder. For all our technological prowess and scientific insight, we are still like people in a vast, dark room, able to perceive only the few objects a tiny flashlight reveals, while the immense, unseen architecture of the room remains shrouded in mystery. We have mapped the effects of these forces, we have woven elegant mathematics to describe their behavior, but their ultimate nature remains one of the great frontiers of human knowledge. It is a humbling reminder that reality is far stranger, more complex, and more magnificent than our ordinary senses could ever suggest. As you go about your day, remember that these unseen forces are at work all around you and within you. The gravity that keeps your feet on the ground, the nuclear forces stabilizing the atoms in your body, the quantum fluctuations that spark the entire cosmic web. You are a living, breathing product of this invisible cosmos. So we turn the question to you, after this journey through the hidden architecture of reality, which of these unseen forces captured your imagination the most? Was it the ghostly presence of dark matter, the cosmic choreographer, the bizarre connectedness of quantum entanglement, or the mind-bending possibility of a holographic universe or a multiverse? Let us know in the comments below. We would love to continue this conversation with you. If you enjoyed this deep dive into the mysteries of the cosmos, be sure to subscribe and hit the notification bell. Our exploration of the universe's greatest secrets has only just begun.